A linear search is very slow because it has to traverse the entire tree to find the data. A hash is a string or other types of data that you fold into a number. A hash table is a two-dimensional array pointing towards specific memory addresses of different points in the tree, and we use our hash number to index into that array.
Okay, what's up, guys? Welcome to today's show. Today we are going to talk a little bit about databases. So, what I want to do is I want to create my own database. So, what are we going to talk about today? We're going to talk about the actual design of these data structures. So, when you design a database, you need to decide how to store the data inside of the memory. I'm not talking about disk space right now. I'm talking about how to store everything in memory. So we have a couple of options, and I have decided on using something called a binary tree, or rather it's my own interpretation or my own design of which is based on a binary tree. So a regular binary tree looks something like this. We have a couple of these so-called nodes. And then we have, let's say we have another node right here. And then we have a couple of leaves. So it's just like nodes and leaves on a tree. And each of these nodes and leaves have different kinds of connectors. So as you see, the nodes, they have two connectors downstream, which means that every one of these nodes can connect to two different data structures downwards. So this node connects to this and downwards to two of these leaves, while this node connects to another node. So it's one additional level. And then we can have, that's not right. And then we can have a leaf right here, and perhaps two leaves connecting to this one. So what are the difference between leaves and nodes? Well, these nodes are the hubs or connectors. They basically make up the structure of the tree, while they don't contain any actual value, no actual data. These leaves, however, they each contain one single element. And these elements could be like one int or one char, but it can also be one structure and perhaps a char pointer with a string inside, and that is what I intend to do. This is the standard way of doing a binary tree, but I'm gonna modify it a little bit. So if we go back to the beginning, and let me select this blue color I had before. So let's start in the middle. Here we will have one node, which is the root node. That's the first node, and it will have the path slash. Then let's say we have 2 additional nodes on each level like this. So the root has a slash as a path, and then this layer or level might have the path slash users. And then down here, this might be slash user slash login or something like that. So these nodes, let me just put the word here, nodes, always go to the left, downwards to the left, right? Then we have a line going to the right from each of these nodes. And here are all the leaves connected. So in the original design, there was only 1 or perhaps 2 leaves per node. But in this case, we may have a whole lot of these leaves. And the leaves, remember, they contain the values. So this is a little bit more suitable for a database, because with this design I may use these paths, these nodes, as a file system almost. So this becomes like folders. So this is the user folder, and this is the slash user slash login or something. So the nodes are the folders containing all of these leaves. But how do we define a data structure of this kind in the C language? Well, as you might have guessed, we either store, at each level we either store 1 out of 2 data structures, either a leaf or a node. So let's create a union. And perhaps you don't know what a union is, but I will explain that shortly. Let's call this U tree. And what does this union contain? Well, as I mentioned, 1 out of 2 things. Either it's a node, and that's a struct S node, let's call it N, or it's a struct S leaf L. So this basically looks like a struct, right? we have this name and we have different variables inside. However, what's different is if this were a struct, then this would take up a bit of the unit of this structure's memory, and this would take up some other part of this structure's memory. So basically we could both define the N and the L at the same time. But in a union, we do only have one of these at the same time. So we either define the N or the L. So this union either consists of a node or a leaf, which makes it perfectly suitable for creating a binary tree with, right? Okay, so let me try to zoom in down here without turning the page. There we go. Okay, so what is a node? A node is as I mentioned before, a struct S node. So it's a structure. What does it contain? Well, as you might remember, I can draw a little basic picture. And we have a link up and we have two links right here. No, not right here, like that. Like this is better. So basically, here is the uplink to the node below, above it. This is a downlink to the node below it. And this is the arm to the right, where we connect all the leaves. So how do we define that? Well, if we begin with this upper one, let's just do struct, and we know it's a node because it connects to another node. So S node, and if we make this quite similar to a linked list. So we use a pointer and let's call it up. And then we have struct S node star, and we have the left. And finally, we have a struct S leaf and a pointer to the right. And in addition to this, I do also want to have a tag. So let's do tag, and that's just so we can define what kind of structure this is. So we can differentiate on the data level between a leaf and a node. I'm not 100% sure that it will be necessary to use this, but let's add it now and remove it in case we choose not to use it. But we do also need a couple of other things. So if I scroll a little bit here, let's say we continue this structure I want to have something like a path. So we can give this a path like slash users or similar, like we did in the example. So let's just do this as a, I'm calling it char now. I will probably call it int8 later on. But let's do char and what should we call it? Folder perhaps, or just path. And then we give it a size, perhaps 255 or something like that. We can decide later. But that would be a regular string containing the path to this node. So we can access it on the user level. The thing is, when the user connects to the database with, let's say it connects just to the TCP port, then it should be able to do something like create and the name of a folder like this. And then it should create one of these structures, link it correctly, and put these users inside of this path. Okay? So this is quite simple. A node just links everything together. Let me zoom in a little bit here. So what's next? Well, we need to define the leaf. So we have a struct s leaf. And what does it contain? Well, we do have a link to the left. Right. I'm not 100% sure that I will use this either. Perhaps I will just point in one direction with the leaves. But for now, let's do this. So this will be a struct s3 because it can be both a leaf and a node. And a pointer, and this will go to the left. So this is the leaf's link. What does it contain then? Well, as I mentioned, every single one of these leaves will contain one element, and one element being a string. And in order to make this effective, I intend to allocate these strings on the heap. So the only thing we will store is a pointer, which we will allocate later on. So char, and this is the well, let's do like this instead. Let's wait a little bit with this value, because first we have the key, because this database will be, each leaf will have a key that distinguishes it. So char key, and this will be a string like this. So a key, and then we have the value as a pointer, which will be allocated on the heap. And we will also need to have a count. So int count, because we need to know how many characters this value will be. The key will be a standard null terminated string allocated like this, but the value should be able to be both bigger and smaller than 255 dynamically. So we'll allocate it on a heap. And then we have the count, and just like before, we will also have a tag. So if I zoom out, we should be able to see all this together. We have a union of nodes and leaves, which we call a tree. We have this part, which is a node containing of the uplink, the left link being the connector to the next level, the subfolder basically. And then we have the right one, which is the first of the leaves in this row. And then we have a path like /users, and we will also have a tag. So the tag will be something like an int value, where 1 may be a node, or a 2 will be a leaf, and so on. Simple stuff. And finally we have this leaf, which contains the left connector, perhaps. It contains a key, and it contains a pointer to a value and a count of the bytes, as well as a tag. And using these two structures, or three, perhaps we can call them, we will be able to create this tree-like structure. Let me go back to this pen, where we have the nodes, one for each level, and we have all of these leaves connecting with an arm like this. So if we were to describe this in computer networking terms, perhaps these nodes would be a router connected like this, and then they have a switch to the right connecting to a lot of different end user computers or something like that. So this is my take on a kind of binary tree with a little bit added to those. So in the next video, what we'll do is we will begin coding on this data structure. We will have a method for searching effectively, and we will create all different types of nodes and leaves and stuff like that. Storing values, finding those values fast, and we will also be coding the actual networking database program. And this is basically all for today. If you like this video and this kind of content, you will be very interested, I think, in this series. at least when we start coding, right? Which is the next episode in a couple of days or so. So thanks for watching, thanks for liking, thanks for subscribing, and I'll see you real soon. Thanks for watching, and thanks for today.
Okay guys, welcome to today's show. Before we start, I just want to mention that on this Friday, the 21st, I will have a live stream where we will create our very own in-memory cache database, like Redis, but faster. That is the intention anyway. And in anticipation of that live stream where we create a database, I will today create a data structure, a form of a binary tree, my own way of implementing it, which will be able to store data effectively. So that's what we're going to do today. And if you want to have more details about how the binary tree is constructed or designed, I recommend watching my last episode where I draw the tree graphically. But today it's all code, so let's begin by creating a directory for this project. Let's just call it tree, like so, and I'm gonna set the home directory to my current working directory, so it makes stuff a little bit easier. And as usual, I'm gonna use Sociopath SCP client in order to alter the files live on my Linux server. If you do this project at home and don't have an external server, that's no problem. Then you just do this locally as usual. So let's see, where did I put it? Inside the temporary directory and tree. So I right click and open in editor. And currently this is just an empty directory. Let me just position this a little bit. Let's see, something like this. And I'm gonna create the files. So we need a tree.h in order to keep all our definitions and stuff. And we need tree.c where we put the entire programming implementation. And I will also create a make file to make stuff a little bit easier to compile and recompile. And I'm going to use this same kind of make file as I usually do. So what do we have? We want to compile tree.o and we need tree.c for that. So we will run cc with possibly a couple of flags. And I'll make this a little bit smaller. I hope you don't have problem seeing this. And we're gonna do -c and the name of the input file, which this represents. Okay, and when we have tree.o, we can compile tree, which requires tree.o. And in order to do that, we run cc with our flags, and then we will do, let's see, we will take the target, and as output file we will have, we will take the source, and as output file we will have the target. So that's a symbol for the target, and possibly we will have some kind of LD flags for the linking process, like so. I will also create a clean, which will simply remove all the O files and the tree binary. And finally we will do all tree. Okay, so that's most of the make file done. And I will just create those variables. So we have flags and we have LD flags. I will leave LD flags empty for now, but I want to compile this using WAll, and let's do O2 for optimization. And let's also define the standard to be C23 or C2X, because this release of GCC was released right before the C23 standard was released. So that's why they called it C2X, because they were not 100% sure if the feature list would have matched the C23 standard. So that's why. Alright, let's save our make file. Let's save our tree.c, and let's save our h file. And hopefully they have been uploaded. They have not. No, I was disconnected from the server. Let's reconnect. That's a good thing with Sociopath, by the way. Even if you have a lot of files open, if you get disconnected and just reconnect, then you should be able to just save again. And let's see, we save this, and we save this. There they are. So let's do make. Okay. I need to do double of this, I think. std, oh no, it should be std equals. There we go. So the only error now is that the file is empty. So let's remedy that. I will simply create an empty main, and let's do hello world, like so. We return 0, and we include std, no, not here. Let's include our own tree.h instead. We save this one, and inside of tree.h we put all these regular header includes. Okay, and if we just do make, we have ourselves a binary.
Hello world. Okay, so that's structuring our project. I will add a couple of more includes. I have 4 which I almost always use in every project. I'm not 100% sure I'm gonna need all of these, but let's prune them off at the end instead, so we don't have to go back here just to include stuff. And let's also include some error thingies. So I want assert, and I also want R number. And in order for them to work properly, I do also need to define GNU source, like so. Okay, so that's a little bit structuring. Now to our real project. So I want to create this kind of binary tree that I showed in the last episode. So basically we will have a, let's see, a couple of nodes. So first we have the slash, for example. In the next level we have another folder such as users perhaps, and then we might have users slash login or something like that, and this grows like nodes in a tree. So we can have basically how many of these as we want. The only limiting factor will be the variable that we store this string inside. When I experimented a little bit on my own, I created a system that only saves this part, so not the slashes. And in this level we only save users, and in this level we save users and login. But I don't think I'm gonna do it that way this time, because what I want to create is a very fast structure based on CPU speed. I don't care if we waste a little memory, as long as it's not extremely inefficient. So if we keep copies of the whole string on each level, it might add a couple of kilobytes at most, and it will make our parsing a lot of easier. So I'll do that, and each of these folders, or nodes as I call them, can contain one or more values. So we might have, for instance, let's say we have users Jonas, we have users Jim, and so on. And those are the leaves. So this will contain a value, for example, and Jim will contain a value. And these needs to be unique in the folder, but we can have a Jonas inside of login as well if we like. So this creates linked lists from these nodes. So basically it's a couple of linked lists, one per folder, each including the value. And then we have the binary tree consisting of this folder structure. Okay, that's a lot of information at once. So how do we begin? It's a rather, what should I say? It's a rather ambitious project, creating this binary tree and make it efficient. So where do we start in a project like that? I like to start with the types. So I will have a type which is called node, and one that is leaf. And those two together
they form a tree. So a tree can be one of two things. It can be either a node or a leaf. And these are structures containing values in the case of leaf and just links to other levels in the case of the node. Alright, so let's start there. I'm going to create a structure which I will call S node. S is how I name my structures. And what do we need for a node? Well, if we think about the links, there is an uplink to the layer above us. And that is always a node, because only nodes can connect to other structures of the tree. So this is an struct S node, and it goes upwards. And if we are at the top, at the root, then this up will point to itself. It will point to this node. Otherwise, it will point to the node on the layer above. What else do we have? We might have a link to the left, downwards to the left. Let's call this left. Or perhaps we shouldn't use left and right and up, but perhaps we should use the cardinal directions instead. That looks a little bit more precise. So let's call this north and this west. It's west, right? West. Yeah. And we will also have a link to the right, but that's not a node, that's a leaf, because to the right or to the east, we're gonna link to the first leaf in that arm that goes to the right. Okay, so there we have our links. We do also need to save our path. And I could make this a char, but I don't like that. I want to create my own, a little bit more precise types or integers. Let's do a type def, and I want to have a 32-bit int. So that is, in my case, an unsigned int, and I'll call that int32. I will also have a 16-bit int, and that is an unsigned short int, and I will call it int16. And finally, I want the 8-bit int, and that is simply an unsigned char. So int8, and the int8 is the one that I'm going to use here, right here. So int8, and let's call it path, and let's do it like this, as an array of 256 bytes. So this will contain the whole path, not just the current level. And what else? We're not going to have any level, we're not going to have any values. So that's nothing to think about. Perhaps we should do this as an U tree instead, because we don't know if, I think I will make the root a little bit different, so it's a node but it's not a node, and perhaps we need to do this. Let's have it like this for the time being, and we'll give it more thought when we need to.
Okay, and we need to give this a name. So type def struct s node, and I want to call it node with a capital N, like so. Okay, so the most of the node is done. Now we need to create our leaf. So struct s leaf, and what will a leaf contain? If we begin with the connections, it will have a northern connection, right? Or rather, it will have a western connection to the leaf on the left, or to the node if it's the first one. So I think I will go back here to, let's do an S node here, but here we will do a tree instead. So struct, no, not struct, it's a union, and I'm going to talk a little bit more about unions later on. So union u tree, and this will go to the west, and perhaps we will have a link to the right as well if there are more values. So it will be a struct s leaf, and it goes to the east. Okay, that's the two links. We will also have a path. So, and I don't think I'm gonna call this a path. No, let's call this a key, because it will be like a key in a regular object type data structure, which this kind of is. And let's say a key is 128 bytes. And we will also have a value, but the value I will not store inside of here. I will just do a pointer to the value. So we will allocate that separately and just point to that value, because the key can be rather small, right? But the value can be rather large. Perhaps we have a big JSON structure here inside of this or something. And it can also be a lot less than 128. So by doing it this way, we can add, let's say, a 16-bit count, or perhaps size. And that is the size of this value. Okay? So yeah, that's basically it. And we will give this a name as well. So type def struct s leaf, and leaf with a capital L, like so. And finally we will create a tree structure, and that's a union. So it'll be union u tree. And what will the union contain? Well, it can contain one of two things. Either it's a node n, or it's a leaf L. And that's the thing about unions. All the different variables in the unions share the same memory space, which means I can only have one node or one leaf, not both at the same time. But in a structure, we can have
everything at the same time. So let's give this a name as well. So typedef union uTree, and we'll call it tree like this. Okay, so let's create one of those structures. I'm going to create functions that do that, but the root of the tree I'm going to initialize using the new tools for that in the latest C release. So I can do something like tree root equals and these curly brackets, and I need to have the definition of the node. By the way, I forgot something. I do also want to have a tag. So tag, and same for the node. So tag. And what is a tag? Well, it's a typedef unsigned char tag. And it can be one out of at least two things. So define tag, or three things, by the way. It can be a root. Let's say we have one, and I usually put the binary representation as well. And we can have a node, a tag node, which will be 2, and that is 000010. And we can also have a tag leaf, which will be number 4, and that's 0100. And if you look at this 1, it goes to the left every time, which makes it possible to have one of these or several of these in the same variable. So this is how we is able to, if we look for a tree, for example, then we have the possibility of looking at this tag to figure out at runtime what kind of structure this is. Okay? And let's copy this into a comment so I can, or maybe we can, no, let's copy it to the comment. I think the screen is a little bit too small for split screens and stuff. Okay. So let's define a root, and we have a couple of different things here. We will have a tag, so we do dot tag equals. It's as simple as that. And what will we have here? Well, we want to have the tag root, but we do also want to have the tag node, because the root is a node after all. So let's do an OR sign right here and do tag leaf. No, tag node. So this can be either a root, or it can be a root and a node at the same time. Okay, that's tag. Then we have north, and north will simply, let's cast this to a tree and point towards itself. So we know if it points to itself, then we know it's the root. Then we have west, and west we will just initialize to 0. Same with the east,
Do we have these? No. Yeah, we do. So east equals 0 and path equals slash, like so. And then we have the tree defined without having to do it inside of a function or anything. Kinda neat. And let's, for instance, print out the address. Let's do %p for pointer, and then we will just, I think we can just say root here. Let's try it out. And let's change one thing in the make file, by the way. So where were we? Right here. I want the standard make command to compile the tree, but first do a clean. Like so. Let's see what it says. Okay, that's a couple of warnings. Probably one of these that creates the rest. Let's see. Type def union u3 expected blah 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 before union. Oh, I misspelled type def. So let's see. This should be in the .h. I want to have this in the on the right. Let's see, where is it? Okay, this shouldn't be here either. Type def, like so. And now probably most of the warnings will have disappeared. No? Let's see. Tree has no member named tag. Ah, right. It's a little bit trickier when we have a union like that, because you see these, we need to specify the N or the L as well. So how to do that? What if we were to just do .n equals, and then we have a double of this? Will that work? Okay, that's better. Initiation of struct as node from incompatible pointer type tree. Right, we shouldn't typecast it to tree. It is tree. We should typecast it to a node. So let's see. This far it has been very easy things to fix. Like so. And let's try it again. Okay, one thing left. Warning, format expects argument of type for star, but it's a tree. Okay, we need to typecast again. A lot of typecast in this project. And this will be it will be a void like this, I think. Cannot convert to a pointer type. Well, let's do it by reference instead. There we go. And there it is. It compiled. And it runs. Okay, so now that we have defined our data structures, let's create a utility function which creates and links up one of these trees. So let's call it, I don't know, create node. And what kind of arguments do we need? Well, we need to know the parent. So let's create one of these arguments like this. And we do also need the path. So that will be an int8 pointer. And we just call it path. Like so. And in order to know, let's see. Well, we can do something like this. Assert that the parent is there, so it's not null. Let's create a pointer for the node. And let's see. We will need something with a size as well, I think. So the size variable, we can reuse that to work with the path as well, if we need to. Okay, so let's see. We need to allocate memory for this one first. So let's set n equal to, and it's going to be a node malloc size. So let's set the size to size of struct s node. And then we will zero out that structure. So let's do something like int8 and the n and the size. And we need to create this zero function as well. So the zero function will be a void function. No need to return anything. But we do need two arguments. And let the first be an int8 pointer. Let's call this the... it would mostly be used for strings, so let's call it str. And then we will have an int16 size as well. And we will simply loop through this string and zero everything out. So basically like the mem set, but I want to avoid using any library functions if I can. And this is a rather simple function to write, so let's also create a int16n. Let's initialize n to 0 and p will point towards str. And we're going to loop as soon as p dereferenced is not null. And then we'll just increase p
and we'll increase n. So we will also, no, let's remove this, by the way. Instead, we will check if n is less than size. That's better. Okay, and for each step of the way, we will simply set p to 0 and then return. Okay, so we have created our structure, we have zeroed it out. What's next? Now we need to link it up. And we have the parent specified. So we'll simply do parent, and let's see, this will be the west. So let's set this to n. So the parent's left leg will be pointing towards this new structure, and then we will initialize the fields inside of n as well. So let's see what we've got. Here is the node. I think I'm gonna copy this into a comment, make stuff a little bit easier. So let's see, we'll set the tag to tag node, and we will set north to the parent. What else do we have? We have the east, which will be 0, and then we have the path. So let's do a simple string copy, and we will need to create cast this to char, and this will be n path. And what will we copy there? It will be the path, and the size will be 255 at most. And that's it, I think. Let's just return n. So we have the tag, the uplink, the downlink, the link to the leaves, and the path. That's everything. Like so. So let's create one of these nodes and see if we can make that work. So let's create one of these pointers, and n will be equal to create node, and the first will be the parent, so let's say root, and the second, perhaps we need to reference it like this, and the second will be the path. So let's say we call this users. We assert that n is true. Let's create an n2. And n2 will be equal to create node, and this time we will set n as the parent, and the complete path will be users login. We'll stick with the same example. Let's insert N2 as well, and then we can perhaps print the addresses of these pointers. So %p, %p, and the first is n, the second is n2, like so, and then we will free n2, and we will free n, and return 0. Let me just check through this create node function if there is anything else we need to cast. So let's see, size of n equals malloc. This size perhaps need to be a regular int. 0 ought to be okay. And yeah, looks fine. I probably forgot about something, but let's go. Oh. Let's see. Create node passing argument 1 from incompatible pointer type, expected node star, but argument is of type tree star. That's right. We need to cast the north link as a tree. So let's just do that. Let's see, north. So this will be a tree because we're not. No, that can't be it. Which one was it? Here we go. Create node. Okay. Expected node. Right. Alright. So it's this one. Let's cast this to a node because the root is also a node, and one error should be gone. Yes. Create node user. Okay, it defaults to a char string. So let's cast this to an int 8. This is the trouble when you are using your own variable types, but I think that it has a lot of positive effects as well. Besides, you become really good at casting after a while. Now it compiled. Let's see. And we have 2 pointers and no error. It works perfectly fine. Nice. Okay, what's next? We can create our nodes. Perhaps we should create leaves then. Why not? So let's just create a leaf star. Create leaf, and what arguments do we need for this one? We will need a path, or do we? We will need a key though, and we will also need a size to that key. What else? The path is included in the key, so that's nothing to worry about. We do, however, need to know the parent. So let's put the parent here as well, and that should be it, I think. Okay, so we need a node N, we need a leaf L, and no, we don't need the N. We do have the parent, so that's not really necessary. However, I want to assert that we do have a parent which is not 0. We need a key and a size. Right. Well, let's begin coding and see where it takes us. Okay, so we have the parents. We know where the nearest node is, but it's not certain that this leaf is connected directly to its node. Perhaps there's a couple of different leaves between. So instead of creating a parent like this, I think we will have a tree, which can be a node or leaf, and this will be on the western side of this leaf. Okay, so let's assert the west instead. And it doesn't really matter to us if that is a node or a tree. So let's create, I will create a variable for this. I'm not sure I'm going to need it, but what do we need to do? We need to be able to find the last leaf. That's a good solution, because it will look something like this. We will have a node, and then we'll have leaf 1, then we'll have leaf 2, leaf 3, and so on. So we need to find the last leaf in the chain, and if we don't find any leaf, we will connect it directly to the node. That's a good solution, I think. Okay, so let's create that utility function. So this will return a leaf, and let's call it, let's see, find last. And do we need to give anything? Well, we need to give a parent, or the nearest node. Let's call it parent. So node parent. Right. So let's assert that we have a parent, and we need a leaf L, and we need a loop looking through this chain. Perhaps we should name this find last linear, because then we can optimize it later on and have like a find last something else, and then we can just alias that through a macro. So something like this: define find last x as find last
linear x. And then we can simply change this one, and we don't need to change every function that calls that function. That's a good tip. Alright, so let's do a for loop. We point L towards the let's see, towards the east of the node. So the parent east. And we will loop as long as we have an L. So let's see, when L is 0, we stop. So it's better to loop as long as L have an east. And for each step, we will set L equal to L east. So one step to the right each iteration. But this will break if we don't have any leaves. So let's check that first. So if parent east is 0, then we will simply return 0. So let's have a function for that, or a macro rather. So we don't need those, and we can just say return error, no error. And then we define a macro for that. I like macros. Define return error of x. And what do we want to do then? We are going to find the backslash somewhere. Here it is. Okay, so let's do two things. Let's change the error number to x. And then we will return, let's return a null pointer. And what is a null pointer? Thinking, do we need to define that? That should be included in C23, but I'm not really sure that they did that properly, because that should be well, an object or a variable which always should be available. There is an include file called std something, std, let's see. So grep ri null pointer user include and x86 something. There, basic file, type def, decal type, null pointer t, C++. Perhaps this is an older
GCC or something. Never mind, let's do it another way. Oh, I shouldn't have closed that window. Where were I? Here, export home equals $pvd, $pvd, like that. And let's create our own null pointer instead. So let's see. Type def null point. Type def void star null pointer and null pointer equals 0. That should do it, right? Right, return null pointer. Now we can simply do ret no error. Let's also set this to 0 at the beginning in case some library call alters it. Let's do the same here. Our number equals no error. And nothing can really go wrong here unless we supply the wrong arguments. Okay, where were we? Find last linear. We want to find the last in the chain. So for each step we don't really need to do anything. As soon as there's nothing to the east, we will break out of this loop, and then L will simply be equal to the last one. We can, however, assert, no we can, yes we can really do that. Let's assert that L is not 0, and then we will simply return L. Okay, so now we have a utility function that will find the last node. So let's set L equal to find last. And what do we need for it? We need the parent. So how do we find the parent? We do not have that. Tree to the west. That could be a leaf as well, right? Perhaps we should do something like node parent, or possibly grandparent. Okay, so we have the parent, the nearest node, and that's all we need, right? Yeah. Okay, so find last, and we give the parent. Then we need to assert that we have a parent. And then we don't need to assert that we have west, because, let's see, no. Okay, So L is equal to find last parent. So after this line, we have defined the nearest no, this is the last leaf. Right. So if this returns 0, then we know we are directly connected to the right. Let's just do this for now. Directly connected, and else L is a leaf. Alright. So before we do these checks, let's create this leaf. So we need another of these variables. Let's call this new, or new perhaps with an L. And let's create one for the size as well. But we have a size variable already. Let's call this count instead. That's more accurate. And this will be a size. And size will be equal to the size of a leaf, struct s leaf. And new will be equal to a leaf casted malloc of size. And we assert that we have this new one. And now we come to this part. So if we are directly connected to our node, then we will simply do parent east equals new. And if we're not, then we will do L, let's see, no, this is to the right, so the east, yeah, that's right, by the way. So L east equals new, like so. And now we will simply initialize the fields of the leaf. As before, I will make a comment and paste this in, because with this font size my screen isn't big enough to split. I am aware of that function though. Okay, so before we do that, by the way, let's zero out this structure. So zero out an int 8 version of new size. And the rest of the fields, let's fill them in one at a time. So we have new tag equal to tag leaf. We have a tree to the west. So new west is equal to, depending on if we did this already, right? New, no, we did the other direction, okay. So if we don't have an L, which means we're directly connected to the node, so then we will do something like this. It will be a node of the parent. Otherwise, it will be a leaf of L, like so. And this is a ternary, kind of an if statement. Okay, what's next? New, and we have done tag, west, east. Then we have the key. Let's simply string copy the key. So let's make this a char, and we will use our key, this one. And we will copy, to the key, we copy our key. And how big is it? Let's do 127, so we have a little extra space, like so. And then we come to this part. So we will also have a value. So int 8 value. Like that. And let's reuse our size variable. So let's set size to the string length. No, let's not, by the way. We have a size as an argument, this count variable. We can use that instead. So what do we need to do? We need to create, let's select this, new value equals int 8 casted malloc of count bytes with 0 new value count times, and then we will, let's see, we will simply string copy cast to char, and it should go to new value. Perhaps we should assert that new value was able to allocate those bytes. So new.value, and the source is also char casted, and it's named value, and how big that will be count. Okay, so what do we have? We have the tag, we have the west, we have the east, key, value, size is left. So new size equals count. Return L. And it is linked up and ready.
Okay, so now we should be able to create a leaf as well. Let's see if we can do that. Before that, let's just see if it compiles. Probably have a couple of errors. It's kinda impossible not to have when doing this semi-advanced piece of code, but it should be fast enough to resolve. Expected identifier, null pointer, return, before return, so 21. This is here. Let's remove this comment. And that changed the lines, of course. Let's run this again. It's still on line 21 in 3. Okay, in the H file. Do I have a yeah, I do. Okay. Line 21. Right. When we define a macro, we should end all the lines but the last one with this, and we should not have a semicolon. Alright. I hope the rest of the errors is as easy. Create node, error, no error undeclared. That's right, I did never declare those errors. And as of now, we only have one. So define no error as 0, like so. And size 16, that's not right. 59. 59 in the other file. 59. Right. This should be a int 16, of course. And the warning, pointer type mismatch, node parent, pointer type mismatch in conditional expression, cast a pointer from integer. Okay, that's another error. Let's see where we had this. Okay, newest equals node parent, and parent is node. Yeah, we should probably, let's see, where were we? Here. We should do the other way around. This should be tree, and this as well. Okay, warning, cast a pointer from integer of different size. The string copy char new value, char value, strncpy. Cast a pointer from integer. How did I declare this? Int 8 value, no?
Yeah, it should be a star here. Okay. This should be an int 8 pointer. And new size equals count L value required as left operand of the assignment. Oh, I forgot one letter. Let's see, where were we? Find last linear, create leaf, and new arrow size. Node star n warning unused variable. Okay, 58. 58. There. Let's remove that one. And now it should compile. There we go. Great. So the troubleshooting has been very smooth and effective today. I like that. Less than 5 minutes per session, I think. Finding this editor, on the other hand. Okay, let's see. Let's test this out then. We have 2 nodes, so let's connect something. Leaf L1, L2, and L1 equal to create leaf, and I don't remember we need a parent, we need a key, a value, and a count. Okay. So parent we have key, so int 8 key and value, and we need the size as well, so int 16 size. So before we create it, let's initialize those variables. Let's say we have a key of, so we're inside /user/login, perhaps it's my user, and the value might be, let's cast this by the way to an int 8, and same here. And what should be the value? Let's just put something, some kind of hex string or something. This could be like a session cookie variable or something like that. And the size will be equal to an int 16 of string length. And what do we send? We send the char version of value. Okay, so now we create a leaf and we connect it to M2, and we need the key and the value and the size. Like so. Let's assert we have an L1. And if we do, let's print something from that L1. For example, let's just print its value. So L1 value. And let's see if, let's begin there by the way.
What did it say? Unused variable. Okay, never mind that. And let's run tree. Assertion L1 failed. Why is that? That means that this create leaf failed. Assert parent. We have a parent. Find last. New equals assert new. Turn L. 103, that's probably down in the main. Assert L1. We should have an L1. If we didn't have an L1, this function's assertions would fail, right? What are we returning? Return the L. And what is the L? Ah, right. We should not return the L. We should return the new. Of course. This is why these assertions are so necessary. Okay, this time it went through, and as you can see, we printed out the value inside of the leaf. But are we able to create another leaf hooked up to the first leaf? That's another story. So how do we do that? Let's reuse some variables. I will create another key. Let's call this John. And we will have a value, which simply will be another string, like so. And the size will be an int 16 version of the string length of the char version of value, like so. And L2 will be equal to create leaf, and this time let's see, we will still reference the nearest node right here, and it will find the last leaf. So key value size, we assert L2, and if it's non-negative we will print. Let's do the key this time. So the key of L2. Let's compile. What does it say? Warning, pointer, target, and assignment. Right, I forgot to do those. So int 8 and int 8. There we go. And let's see. We get John, we get this, and no error. So everything we have coded today has worked very fine. This is as long as we can go on in this episode. It's probably a lot more than an hour anyway. If you like this episode, there will be more in this series, and I hope you can like and subscribe to the channel. And on Friday I will have a live stream where I code the networking part of the main database program in C. So if you like this one, you will like the live stream even more. I see you Friday. Thanks for watching and thanks for today. Okay guys, do you hear me okay? Okay, so we are live. And let me just make a little bit of announcement. So let's see if you see my web page. 1 second. Here we go. This. All right. So I'm just gonna type something like "We are live. Join you too." Something like that. And then I should be able to click this one and that and so. There we go. So last time I had a stream, we had a little bit of a bandwidth problem, most probable due to my Wi-Fi connection. So this time I have connected through cable, and I hope that everything is all right. And according to my my indicators, the quality should be good. What do you say in the chat? Is the sound okay, quality-wise? You can write in the chat if you... Okay, good. Hello, Noel, and hello, Robert. Hi, Arnob and Angel, and Through Float. Hello, hello. Who else do we have in here? A couple of other people who hasn't written in chat yet. If you want me to greet you, you can also write in the chat, because I don't really see a list of all the users, unfortunately. So the first few minutes I want to dedicate to just talk to you guys a little bit, because last time I had a stream, there came a couple of users when the stream started, and after 5-10 minutes a lot of other users came in. So I don't want to start the real project until like 10 minutes past the original start time or something like that. Sounds fine, guys?
Hello, Nob. How are you? Okay, great. Very good. And as you all guys know by now, Angel is my trusted moderator, and he will keep external spammers away. And a little later, because I'm thinking that we are gonna have like a schedule, something like this. So at 90, let's do 00. So 00, that's the time when the stream started. So it's 1900 in my country, Sweden, but it might be quite different for you guys. So let's say that 0000 is when the stream starts. And I'm thinking the entire stream will be perhaps 3 hours, something like that. And I understand if you don't can dedicate 3 hours, but I hope you can, and you can always watch the recording, which I will release in a couple of days. But I really enjoy you guys being here live with me. So the first hour and a half, we will focus on the main project, coding the database. Then in the middle of the stream, so approximately 01:20 or something like that, after 1 hour and 20 minutes, we will have a 20-minute break. And then after the break, we will dedicate 10 minutes or so at some other stuff, or maybe I should say other announcements. And then from this to something like 0300, we finished the project. Okay, is this schedule understandable? The time at my place, it's 7 in the evening, so 1900. Okay, so it's middle of the night in the Venezuela. I'm happy that you are here, even though it's the night, Angel. And you're from India, Arnav. India is my biggest audience, actually. When I look at the statistics for my regular episodes, almost 20% or something like that is from India. I really like India. It's a beautiful country, and Venezuela as well. I haven't been, but I will go someday. Alrighty. So, what else? Yeah, I have one pretty big announcement myself. I have quit my day job to focus 100% on YouTube from now on. What do you say about that, Internet? I'm glad to hear it, Arnav. So before, I think you all know that by now, I worked as a instructor and an consultant for programming and network technology, and I've been doing so for like 8 years, and before that I worked in network technology. But now I will focus on YouTube. So what do you think about that, guys? Arnab, I will do something like that actually. Uh, I am I am coding a platform where, well, all my episodes will still be 100% free. That will always be the case, okay? But I will create a website where you can uh, pay for the episodes if you want to. So it's voluntarily, you know. So if you go and watch one of my episodes and you think that you have learned something and you like the episode, then you can voluntarily, if you want, give a small sum of money to me. Thank you, Robert. Yeah, I think so too. So how many users do we have? I'm not really sure if I can see that from here. Okay, 6 people at the moment. Perhaps. Okay, so the time is 19:15 here. Let's start talking about the new project. 1 second, I'm just gonna look for my image. Never mind, I'll do it another way. Okay, so are you ready to start with the project, guys? Let's just do that. Let's see, and now my chat disappeared somewhere. Sorry, one moment. Okay, it went here. There we go. Okay, so the project will be something like this. I want to create a database, my own database, and my intention is that it will be very, very fast. So I'm gonna call it Cache 22. It's a pun based on the, catch 22, but it's a cache. So it's an in-memory database. An in-memory database is not saved to disk. If you restart the database, you will lose all the data. So it's basically like a RAM memory, and it's saved in the RAM only. And why would you need such an construction? Is there perhaps anyone in the chat who knows that? Where did you go? So chat, do you know what use you might have of an in-memory cache database? Thank you, Tejas. Anyone who's made any web development, perhaps? That's right, Tejas. And what kind of context or what kind of projects would you need such a thing for? Because most often you want your data to be saved when it saves in the database, but not always, right? So the idea is the following. If you do any web development, for instance, and you have a login procedure. So you have a couple of users and they log in to your website. The user information, like the usernames and password and of such things, they need to be saved in a regular database that writes to the hard disk drive. That's right, Arnab. So Arnav says if there's no DB updates, we fetch directly instead of calling the DB again and again, useful for multiple read operations. Exactly right. So we use the cache database as a step in between the regular database, so we can easily grab our data if it needs to read the same data again. Very good. And there's one other case as well. So if you have the login information saved in the real database, when the user logs in, they get a session ID. That's something like this, just a random string, but that identifies the login, so to speak, that connects your web browser. So web browser, it connects to the server. So every time you send a request with your web browser, you include this session ID as a cookie. And that defines your connection, so you don't have to log in again and again. It remembers that you are logged in. And that's exactly that kind of temporary information that you benefit from having in a fast in-memory database, because as soon as you have logged out, this information is deleted. And if the information would be lost, like if we have to reboot the server, that's not a complete disaster, because all you need to do as a user is log in again. So that's a very common use case as well for an in-memory database. And the most known or used memory in-memory database is called Redis. And that's what gave me this idea. So, one sec. So I was looking at Redis website, and I found something peculiar. This. Get the world's fastest in-memory database from the ones who built it. So when I saw this this sentence, I thought, well, what if we could do better? So the entire goal of this project is to make it faster than Redis and force Redis to change their website and write from the almost fastest or something like that for the second fastest. Wouldn't that be fun, watching they rename that slogan just because we coded something together which is faster than Redis? And that's right, Angel. Exactly. We can have replicas of the original disk DB to query data quickly. That's exactly right. That's a different use case for this database. So it's really useful, right? This kind of database, and it will be fun to code, I think. Okay, so let's start coding then, right? And you can follow along with me if you want to. And let's see. Okay, that's very interesting. Redis is not free anymore. Okay, so we are making our database completely free, which means that's another selling point, so to speak, for our database, right? Anyhow, let's get to the coding. And are you seeing my whole screen right now? There's nothing at the edges that is outside of this black window, right? Because we'll be doing most of our code right here. But before I begin, I need to log in to my Sociopath SCP client, so I will be able to code on the live on the server. And it almost doesn't fit, but yeah, it kind of does. And if you haven't used this tool before, then let's see, this. If you haven't used this tool, you can go to Google and Google Sociopath SCP client, And why does it have the name sociopath? Well, that's because it's an SCP client, and I think it's a fun pun to go from SCP. And then you should come to a page similar to this one. And it's completely free for educational use and for, well, everything non-commercial. All right? So I will log into my server, and this works on every Linux server by default because it uses the SSH protocol in the core, so to speak. And I will create a new temporary directory, which I will call cache 22. And then I simply right click to this and open in editor, and then we can live edit it directly from VS Code. So it created a new window. I need to kind of resize this a little bit, I think. Something like this. And let's minimize this. One trick is to click on one of those and then click outside, because if nothing is selected, then the TCP keep alive kicks in, which makes this connection will almost never disconnect, which is kind of nice. Alrighty then. I think I need a little bit more space, like so. And what kind of files do we need? Well, as usual, we will need a make file. So right click on the folder, new file, and let's call it make file, like this. And all these annoying pop-ups, which I don't know how to remove. And let's call this cache 22.c. And an annoying pop-up again. And cache 22.h. And yet another annoying pop-up. Isn't it wonderful? I wonder who might have coded this. Can it be Microsoft, perhaps? King of that kind of stuff? Never mind, I like this editor. It's a very good editor. And let's just put some temporary stuff in here. Cache 22.h this is. And I want the C file first. Okay, it didn't. Oh, there. And then I want the H file, and last I want the make file. So let's just put something in here for now. And in the C file I will do a comment as well, cache 22.c. And now I have saved all three of them. So if I go into this, I need to log into the server first. Let's start my screen. And this will be 367 perhaps. No. Here we go. this is used for other stuff. Let's just create a new screen like so, and I need to disable the visual bell off. Otherwise, when I do like backspace, it will flash the screen. Totally annoying. And what is the screen, by the way, the program I'm using right now? Well, I can have multiple windows, like in the terminal, as you can see. These are two different windows that I'm altering between, and you alter with a special command key command. And if you get disconnected from the server, you can reattach to the screen and continue where you were. So it's very good. I use it all the time that I'm involved in some kind of Linux or Unix system. It's named Screen, so I recommend it. And it's not my own code, by the way, that I'm promoting. It's I just like that one. Okay. So let's see, where were we? Look, inside of the temp, we created a new directory, cache 22. I will set this to my home directory temporarily. So home equal current working directory. And now the path, or the prompt, which was this big before, is only this big. So it's a little bit easier to handle. And as you can see, we have all our 3 files, and they update automatically. So let's see, where were we? Well, let's begin by creating the makefile, so we make our lives a little bit easier. And annoying that it resizes the entire window when I resize the size of the actual thing. I mean the font size. Anyhow, what are we gonna compile? Well, we will create a cache 22.o, which has a dependency which is cache 22.c. And how do we compile this? Well, we'll run our compiler, and we include a couple of flags, and then we add the flag -c, so we compile this to an O file, and then we will specify our source file. And source files in makefile use this dollar and caret symbol thingy. That is the source, and you can remember it by looking at this as an arrow. Okay, and why an arrow? I will get back to that. And the next step, then we have our cache.o, but we want to create our cache, so we will add cache.o as a dependency. And how do we compile this? Well, we run our compiler, followed by flags, and this time we specify our source file -o our target file. So this is sourced, the arrow, right? And this is the target. This looks like, if I zoom in a little bit, this @ sign kind of looks like a what's the name? Well, the target that you shoot against. If you shoot arrows, or if you shoot with a gun at a board, you shoot at something which looks like this, right? So that is how you remember. This is the arrow, and this is the target. And in addition to that, we might have some which I call LD flags. That's some additional flags which might be used to link the thing. Not necessarily used though. And when we just do make, then it will run the all thingy. And what do we want to make? Well, it's just one thing at the moment, and that is the cache 22. Let's rename this, by the way, cache 22. And I will also have a clean which removes everything. So it will remove all the .o files as well as the cache 22. And I want this clean to be run every time I run this. And all that's left to add are the flags variable, which I think we will optimize with .o2. Let's add w_all so we get a little bit more warnings. And let's also specify the C version that we want to run. And I'm going to be using C2X, which is basically C23, the newest one. Okay, so save this. And if I have done everything right, then I should be able to run just make and only get errors because the files are empty and nothing else. And no cache.o. Interesting. So what do we have here? Cache 22.o, cache 22. Oh, I just did cache here. It should be cache 22. Easy mistake. Let's try it again. And this time it works. It creates our O file, as you can see. And also it gives an error because the files are empty, but that's what we want. And if I do make clean, everything is clean. So we have the structure of our project as of now, but we also gonna need a couple of things. We will need our tree, but our tree isn't finished yet, right? So what we're gonna focus on today, which will be big enough, I promise you that, we will create the base database server, okay? So today we create the core database server, and we create all network communications and stuff like that. So my intention is that you should be able to connect to the database, issue commands, and those commands should be interpreted, and it should call the correct function. Okay, but before we begin, do you have any questions? Okay, the chat is a little bit empty. I hope you can still hear me and that everything is okay. Okay, there we go. I think it's a little bit delay when I say something and when it happens on chat. Will it support the Redis protocol? No, it will not support the Redis protocol because we will be coding our own. However, what I intend to do when the database is finished is create a JavaScript library which uses the database, and the API will be exactly like Redis. So you can use the JavaScript Cache22 API the same you would the Redis API in your web development. My protocol, I'm going to describe my protocol. One sec. So I think I'm going to do something like this. So there are basically two ways of defining a network protocol. Either you define that these two bits should mean this, and then after that you have 4 bits, which is like something else, and so on. And this is the popular way of doing it today. So you basically define a structure with all of these fields, and then you send that to the database, and same with the reply. The advantage of doing it this way is it's slightly more optimized because you make use of every bit every time you send a message. But our project is not intended to have the best possible network protocol. That's not where the speed comes from, and it will not be the most memory preserved one either. No, we will focus on CPU optimization, because that is what will make our database fast, that it utilizes very few CPU instructions when you need to grab some information. So I have decided that my protocol will use ASCII. So basically you will be able to do telnet and then localhost and some port like this, and the database will say something like hello, running Cache22 version 0 or something like that. This will be customizable, by the way. It will not give out this kind of info if you don't want it to. And how do you reply when... Well, you will have a client, by the way, which will help you do this. But the actual protocol will look something like this. So the client will say something like create users. So it will create the folder users, and then you get back something like 100 or 200, okay? And then you will create, then you do something like insert users key value, like this. Or you do something like select users key. So it will be a very simple ASCII based protocol, but we will not lose many bits on each transaction, and it's much easier both for me and the user, if they are advanced enough, to troubleshoot if something goes wrong, right? Because they can just telnet to the server and issue the commands to themselves if they want to. But we will have a client, command line client, which will send these commands and have like a real terminal and stuff like that, which is necessary nowadays. If you have any questions, you can ask them anytime. I will not be able to see them and answer them when I'm coding, but my dear moderator Angel will collect them, and every now and then I will ask, are there any questions? And then Angel will forward one question at a time to me. Okay? So, it's time for the actual coding then. Let's see, where is this one? Here we are. And it's very big at the moment. If I do this, can you still see this? Is it big enough? Maybe I can also, but this is too small, right? Okay, yeah. Let's see. So, yeah, let's keep it this big until we run out of space in the x-axis, because I don't want to have to continue on the line below, you know. And we can remove this one as well, because we have all our files open, so we have a little bit more space now. Okay, so where do we begin? Let's start by including our own include, that is cache22.h, and then I will just create a small regular main process as usual, and let's print something like okay, and we return 0, like so. So we have something, right? And in our H file we will create a couple of includes, and I like to include 4 different include files that I always use in almost every project. And then if we notice that we're not using one of these, we can just prune them off, right? We don't need to do it all the time. Okay, so let's save and just verify that it works. We do make and we run our program, and it's okay. So we have a basic program, right? So let's continue by continuing the code, and let's think for a bit. What do we need and where do we start? This is a rather big and ambitious project, right? So where do we start a project of this size? Well, we have already started with the basic internals of this program when we created our binary tree, right? But that binary tree isn't done, so we're going to focus on the other part of the program, which is the actual server software and the the network communication, right? So let's start by creating the basis of the network communication, and so we can log in to our server to start with. Okay, so how do we do that? Well, we do need a couple of standard structures. We need a struct, let me see, sock, sock address in, and we need, let's start with one of those. We need one for the client and one for the server, by the way, but I'm gonna handle the client in a separate function. And we should probably not do this inside of main, by the way. So let's instead do something like, while and we need a global variable. So let's say we have a variable which is a bool, and let's call it continuation, and this is the server continuation. So s continuation, and the s continuation from the start, s continuation, will be equal to true, and as long as the continuation is true, we will loop our main loop. So when we quit the program, we set s continuation to false, and it will quit the program. So while s continuation, we will run our main loop, like so. So we get a little bit structure. And as I create the functions, I want to add them inside of the h as well. So let's do and we need the bool as well, std bool.h. Where were we? Yeah, with the function declarations. So we have an int main, which takes an int and a star, and before that we will have a void main loop void. As of now, we might add something to this. Another thing I like to do is define my integers, because I usually use 3 different integers. So I will define a type def. I want a 32-bit integer, for example, and that would be an inside int 32. I will also need a 16-bit integer, which will be an unsigned short int 16. And finally, I will need an 8-bit integer. And an 8-bit integer in this case is a char. So int 8 is char. Something like this. And that's basically so I have a little bit more control over the size of the variables, right? So let's see. Okay, the number of viewers is increasing. That's a good sign. 10 looking at the moment. It was 6 last I checked. Hope you like what you see as far. Okay, so where were we? Our main loop, right? And this will be a void main loop. And I leave this like this. Do you know, by the way, what the difference is between this and this? You would think void, that's nothing, right? So it's basically the same. Well, the difference is if I have a void, it's wrong to call the main loop and do something like 1, 2, 3. That's not okay. But in case of empty, we can give them as many arguments as we like. You didn't know that, right? Anyhow, that's a parenthesis. Let's go back to where we were. So struct sock address in sock. We also need an int s to hold our file descriptor. Okay, so we have a question. And the question is, if the CMake file on Microsoft Windows can use the GCC compiler. I would assume so. I have heard, I don't know much about CMake, and I don't know much about Windows in general or Microsoft stuff. But I have compiled programs, I think, in Linux which were coded in C, not my own, but other people's programs, and they used CMake. So I'm not 100% certain, but I think at 95% certain that it will work. You might have to tweak some settings though. Okay, so where were we? We were in the VS Code, right? Okay, so now we have our structure. Let's begin by preparing our structure, and there's 3 fields in there that are interesting. We need the SOCSIN family to be AF INET. That's basically a standard thing that we're using internet protocols. Then the next thing is our port. And what should that be? Well, we need a function which puts the data in the network byte order. So if it's, for example, in hex FF55, we need to do 55FF. And in one of my episodes, I coded my own function for that, but we're not going to waste the time on that today. So instead, we're going to use the standard C function ageTOM_s, and we put our port right here. Yes, or perhaps, yeah, let's do it like this. So inside of here, let's define our port as, what port should we use? Any suggestions? It can be basically any value from 0 to 65,535. Any suggestions? Well, let me define this as something for now, 12,000 or something. And if you have any wishes, just say so and we will change it. Because the port number when we are designing network protocol server programs is like an identifying factor to your protocol. It's unique usually for your protocol. So let's select something beautiful, right? And what else? Well, we will have to define where to listen on that port. So let's do 120 and 49. Okay, I think it needs to be a number which is easily to remember by the admins. If not, then nobody will care, right? So I think a 4-digit number is better, and something which is easily remembered. But thank you for the suggestion. Okay, so let's do define host, and we want to listen to localhost, which is 127.0.0.1, like so. We go back to our C file and we do the SOCSIN address, source address, and we use a function called inet address, because this too will have to be changed to network byte order. So an IP address looks like this in hex, and we need it to look like this. So that's because the internet wants all the important data to be sent first. So that's basically why. But we use this inet address function in order to convert So all we need to specify is a string, and let's define that as a constant for the time being. I'm going to change it to command line arguments later on. So what did we call it? Host, like so. And now we have successfully filled in our structure. Next step is we need to initialize our socket. So let's do s equals socket, and we pass AF inet sock stream. That means it's going to be a TCP connection eventually, and 0 at this last field. That's always zeros when you use sock stream. Let's check if the s now I remember I need to have an include assert.h and also the error number.h. And if we're going to use all of those functions inside of there, we have to define this odd GNU source definition. Otherwise, it will not find our functions that we need. And by the way, let's check what h-tone-s needs for including. So we do man3 h-tone-s. And as I have told before, when you are trying to look something up, when you coding functions, start with a 3 and do h-tone-s. If it fails, like if you do select, for example, then it fails, then you select 2. That's the best way of always finding the correct information. So this time it wasn't select we were after h-tone-s. And let's see, we need this include, right? So let's go into our h file and add these. Let's do these together, and then we have all of this network stuff for one own section. And we also need inet address. So these 3. Here we are. So that and this, and this was a duplicate, so let's remove that, like so. And which reminds me, I want to have some protection against duplicate stuff in my H file as well. So if not defined cache 22, then we define cache 22 cache 22, and then we do all the rest of stuff, and at the end we do end if. So why do we do this? Well, the first time around cache 22 will not be defined, so we define it, and then we do all this stuff, end if. Next time, if you include it twice, then cache 22 will be defined, so it will not do all of this again. It's a quite smart and standard way of doing this. Okay, so we create our socket. If that fails, we will quit the program, right? So it shouldn't fail. If this fails, something is very wrong. So assert that S is positive. Let's just double check the return value so I'm not lying to you. Man, okay, let's try my thing here. So we need to check out the function socket, right? So let's begin by doing man3 socket. And we don't get a hit. But if we do man2, we do get it. Because if you do it the other way around, you will sometimes get garbage. And if you don't leave out that number, you will a lot of times get garbage. So remember this order of events. Return value, that's usually down at the end almost. So let's see. On success, a file descriptor is created. On error, -1 is returned. Okay. So assert that S is greater than, let's do 0, because it should never return 0 either, then something is really odd. Let's do it like this. Alright, so everything works as of now. The next step is to bind this socket together with this structure, right? And we use a command called bind for that, and it takes the socket file descriptor as its first argument. The second argument is our sock, but we need to cast this to a struct sock address star, and we send the reference. And as the third argument, it's just the size of sock. Okay. And what is, I think bind is a little bit reverse when it comes to return values. So man, let's do to bind instantly because I know it is. And let's see the return value. Yeah, on success 0 is returned. That's a little bit odd, right? But that's just the way it is. So let's do an if clause. So if bind sock address is not 0, then we will fail by doing assert p error number. So this basically checks the error number, which comes from this. Perhaps we should reset it first, and then it basically quits the program with this reason. Okay, so it's a combination of print error and assert, and it's a standard function, believe it or not. That's why we need that super weird definition. Alright, so the socket has been bound. What else? We need to listen on the port, right? So then we use the listen, and we just specify the S, and this is how many connection we will keep in queue. So if we do 20, we can accept the 20 connections at a time, basically. And that will be enough, I think. We can begin there anyway. When we are completely done with this program, this will be customizable, of course. Let's see. We have something in the chat. Your subscriber count equal 4. That's quite funny, actually. A little bit tricky to update it every day, though.
I suggest port should be indicated when running the server. Not specify, we can place one by default. Okay, Robert, I didn't know that. That's actually pretty good. Let's do that. And Angel's thing as well. Okay, so that we can do quite instantly, I think, if we will just go to VS Code, and we will write inside of our main function. I will create a char export. This is a port in the string format, and we will also have an int, which is a port. An int 16 is enough, by the way. So int 16 port. If arguments is less than 2, then we haven't specified any port, so then we set the port to the default port, which we, by the way, will change to that prime number thingy, like so. And let's see, so if the arguments are this low, we will do this, and else if we have a port, no, let's just do this. Else port equals argv1, then we will set the S port to the int 16 representation of let's see what it's called, A to I. And what will we send? We will send the port like this, and then we need to send it to the main loop port. Oh no, the S port. Let's set the S port. I'm doing it the wrong way. The S port should be set to that, and this should be the S port, and here we will send the port. That's right. Okay, so the main loop will accept an int 16 port, and we need to update our function definitions. So instead of void, we will have an int 16 right here, and basically change this to port, right? So before we continue, let's check the return value of listen. I don't think it's something to worry about, but let's just see. Okay, some stuff can go wrong anyway. So on success, 0 is returned once again. So then we will do, let's do like we did before. So if listen S20 is true, then we will assert p error based on our number, and we need to reset that to 0, like so. And let's just try our program before the break. So there's something wrong at, a colon instead. So let's see, where were we? Inside main, I think. Oh, I forgot one there. Is that one? And we enter down a couple of times, and we do make again. No, 26. Okay, in the H file. So let's see the H file. We scroll up, and we look. Oh, there. Let's space down and clear and make. And now we only have a warning. Assignment to char from int. That's right. We need to save this as a... where were we? Here. We need to save this port as a string instead. And let's run make, and it compiles, and we run the code. And where did it fail? Address already in use. Okay. Address already in use. So it basically say that we already have a service on that port, right? That's that dash and direct dash y 12049. Did we specify the address erroneous somehow? Let's double check our code. So 127.0.0.1 and sock sin address s address equals inet address host, and host is 127.0.0.1. So the socket called, let's do an strace of this. So where were we? Catch 22 strace dash f. Okay, what is going on here? So here is the error message. So what happens before that? We run bind, which generates the 4, okay? And AF inet, sock stream, IP proto IP, binds SA family, AF inet, in port, H2 S 12049, sin address, inet address, address already in use. That's a weird thing. Let's check the man page for that. The given address is already in use. If we run ifconfig ENS 192, no, hello. Let's do. Oh, so we can just do this. Has been ifconfig. Hello. 127.0.0.1. Let's check one thing, by the way. What if we were to run this temporarily on any host? So instead of inet address host, we just, can we set this to 0 perhaps? Or do we need to typecast that? Let's see, 369. No, that's not right. 367. where were we? 36. Okay, it's here. So cd temp, cd cache 22, and make. Okay, it compiled. What if we change that port then? Does it change things? 120.49. If we were to do 25,000 or something, what happens then? Address already in use. I must have done something wrong when I prepared the structure or something. Let's see now. You can do one thing 100 times but still make mistakes. So socks in family AFINet, socks in port HTON S port, sock sin address S address equals 0, S equals socket IFINet, sock stream 0, and bind. So if bind is not 0, struct sock headers in sock, size of sock, assert PR. And bind should be 0, right? Let's double check that. Bind to bind, and because it returned 4. Did you find something wrong, Arnab? On success, 0 is returned. Yeah, I did have that before, instead of the 0. But 0 is any address, right? We can also, to be more specific, we can do something like this. INET. I think it's something like in address any. There should be some kind of variable like that as well, but that shouldn't be the problem, I think. No, whatever we do, it gives us this strange thing. Let's check, by the way, if s-f let's 2t and 1. Let's check for the socket call. So it gives us a real socket. But the bind fails. Address is already in use. Let's see, do we have any example code we can use? Web server. Or maybe something is wrong with my machine. What if we run this as root? Same error. $25,000. Maybe it's, but that shouldn't be it. But maybe let's try something. What if, because we are sending a int16 value currently, what if we were to cast this to a regular int? Maybe that's the error. but it was a very bad. Oh, sorry. We were in temp and we were in cache 22. Make this. No, that's very weird. Address already in use. I've never seen such a thing. Did we forget any step? Socket, bind, listen. You know what? We are past the schedule, so let's take our break now and we continue troubleshooting in 20 minutes. I will while we are having a break, I will see if I can find a solution as well. Sounds fine with you, chat? 14 and 15 line. I just need to check this real quick. 14 and 15. Well, that shouldn't be a problem, really. The problem is that bind doesn't give. Never mind. Let's do the break. So I can do something like if I. Let's do this. 20-min break. Be back soon. And okay, so we see you guys in 20 minutes.
Do you hear me now? Do you hear me now, guys? Okay, great. Because I muted my microphone when I went on a break, physically on the microphone, and then I unmuted it. But the computer muted in the software as well, so I needed to activate that. But all I was saying this far is the arrow we had before. Well, we have a main loop, right? And then the main loop is an unfinished function because we are in the middle of it, right? So what happens here? Well, we bind to the socket with the address, and then we exit, or then the main loop is done. So then the main loop function will run again, right? Because it's a main loop. So the next time the bind runs, it will fail, because then the port is no longer free. So it's quite embarrassing, but well, you know, that happens. So if we simply do something like temporarily s continuation equals false, so we don't want to continue. And if we now were to compile this stuff and run it, it works, right? Because it shouldn't output anything if everything works. If something is bad, it will output the error. So yes, the problem is the main loop, right? Because we have an unfinished function, but now it works. So basically we need to finish this. I think we're gonna rename this one, by the way. Let's call this init server. And then we will simply have a, let's put it here. So we will have a main loop as well, in 16 port, and inside of the main loop we will run our init server. So this should only be run once, right? So we put it here instead. We give it the port, and let's see, port, and then we don't really need to give the int port, int main loop. We don't need to give an argument right here, and not right here as well. But we need to define our init server where we give the port, something like this. And now we can go back to using localhost and the port we had before, 120.49. And let's see. We need the s, by the way. Int s. Int. So let's see. We do init server, and then we should return the s from here. So let's do where were we? Right here. Init server, and inside of our main we do an int s, and s equals init server, and then we pass the s to the main loop. I think this is a better way of doing these things. And let's put in a message which says that everything is fine. So something like print, or let's do log, by the way. We'll create a macro with that name. So we will log that server listening on this and this. And this will be our host and our port. And then we will return the S. Yeah, exactly right. So let's see. What else? Yeah, we won't be using init address anymore. Instead, we will go back to this. Right. Like so. Let's see if I did anything wrong. Oh, yeah, log. We didn't define log. So what is log? It's basically printf, right? Yeah, but not quite. So define log. Let's just do log with small letters. And we will log an x and some arguments like args. And what are we gonna do with this? Well, we are gonna call printf, and we will have the x right here. This is the what's it called? The format string, right? And then we will possibly have a comma, but only if we have args. So then we have something called va opt. This is new in the latest C, I think, which means it will only, I think it should be like this. It will only add this comma if we have args. Let's see if I did that right. And I think we need to define std_def.h and not define. Include. And we also need to include std args like so. Isn't it std_args? std_arg. I think it's singularis. std_arg. And what did we miss? Conflicting types. I didn't update the types. So void main loop, and it takes an int init server, which takes an int 16. And what did we do? Void main loop
takes an int. Int inet server takes this. Okay, let's try again. It didn't like that construction. VA. Let's wait a little with that. I'm not feeling too eager to define that. I probably will always use it with args anyway. So let's do it like this. And now it can pass. Does it run? It didn't print anything. Perhaps we didn't fix that last loopy thing. So let's see, where were we? I need to make it a little smaller, just temporarily. So port is the A2I port, then we set S to init server with that port. And what does init server do? It runs through all of these things and it should log this stuff and return the S. And then I think everything is right, but it didn't print this thing correctly. X args. What if we were to do just those right here, and then args like so. I renamed it, didn't I? Log with small letters. Did I change that here? Log. Where did you put it here? Yeah, I kinda did. If this doesn't work now, I will just throw out this log function. VA args. Same problem that we had last stream. I thought I fixed that, but never mind. And that way we changed it to one of these, right? VA args. Let me just try this one more time. We are probably missing some include, but never mind. We can use printf like normal people, right? So let's remove this for now. And we go back and we just do printf. The general idea between having a regular printf and a log macro is we can define something that doesn't show these log messages if you're not running in debug mode. So that's basically why. But let's skip this for now. Make, now it works, and why does it do this? BRK. It does print it, right? It should at least. Perhaps we need to flush it. Yeah, now I see what's wrong. If we look at this printf, I don't end it with a new line. And if I don't end it with a new line, it doesn't get printed to the screen until it either gets flushed or it encounters another new line. So one way of fixing it is adding this new line. We could also have done a flush std out like this. So now it would work 1000% certainty. And there we go. We have a listening server, you guys. All we need to do now is accepting connections and handle that input. But before that, I promised you something else, or I mentioned something else. So, are you still with me, chat? Let's see what happened here. I remove the cast int on the port variable. I think I will keep the cast though, but in my case, because I have defined my own variable type, which is int16, and even though the cast might not be necessary in this specific case, I like doing it to showcase that. Okay. Alright. So now everything works. Well, we need. I need to tell you something. As you know, Angel has been a moderator for us, and I have decided to promote him to a chief moderator because he has done a great job. And this means that he will be allowed to employ, so to speak, to regular moderators, which he will be the boss over, so to speak. So, Angel, do you have any special someone that you want to offer the job? Do you guys still hear me? Maybe it's a little bit delay, I'm not sure. Do you other guys hear me? Is it some problem with the sound? Does it... I don't know, do you hear me, for example? Alright. When Angel comes back, please notify me and we will take this part then instead.
We will never close the socket actually, or we will close it when we exit the main loop, and that's only when we shut down the server. So let's add that next. It actually does do that by default when you quit the program or press Ctrl C, but it's good to have here. So let's see, we do have the S, so let's just do close S when we shut down the server. Like so. And yeah, so next step is to accept the connections, right? So let's see, and that we will do inside of the main loop, because we will accept one connection and do something with that, and then we will accept the next connection, and so on and so forth. So we will need an additional. Okay, Angel's back. Okay, Angel, good to have you back. I was just mentioning that you have done a great job, and I have promoted you to the chief moderator, which makes it which means you will employ 2 of your moderators, and you 3 will form a group where you will be the boss. So I will keep coding, by the way, but while I am coding, you can take care of this part, Angel, and offer someone or 2 people, up to 2 people, the job. All right? So let's go back to the main loop. Sock address in, which is a struct, and let's call this client. We will also need an S for that client, so let's call it S-client. No, let's just do S2. And we will use the accept command to accept connections. And the first will be the main S, which is the file descriptor for the server. And then we will specify a sock address structure that will be empty from the start, but it will be filled out with the IP address and port and stuff by the actual accept call. So in order to handle that a little bit better, I will create my own data type which will store that information. So it will be a very simple structure. Let's call it S-client for struct. And what do we need to keep in here? We need the int s, the socket file descriptor for that client. I do also want to store the IP address of that client in a regular string variable. So let's do IP, and how big is an IP address in that case? Let's take the biggest possible, and it has 4 times 3 fields, which is 12, and then 1, 2, 3 dots, so 15, and then the invisible 0 at the end. So 16 should be perfect. And what else? Perhaps we will have use of storing the port as well as an S, like this, and perhaps even more things. But let's start with this, and we will do a type definition of our new struct as client, and we will call this a client with big C. I did the close, right? Here. Okay, so let's see. Okay, so we will accept the connections, and let me just check the return value of the accept system call. Right, we have a third variable as well, at least. Let's see. Okay, we need a pointer to somewhere to store the address length as well. Right. So let's check the return value at the same time. So on success, it will return the file descriptor. On error, -1. Okay. So it's here. And the second argument is the client structure. So struct sock address star, and we give the client, and then we give the, let's call it len for length. And what is len? It is a int length, and we need to send a reference to that. And if everything goes wrong, it will fill out these two structures. So we have the length of the address, and we have the address, so to speak. So let's create a char IP and an int 16 port to temporarily access that, and we will check if this returns less than 0, and if so, what will we do? We don't want to exit the whole program, right? Because this can just be a temporarily the server is temporarily full or something, if there's a big flow of connections. So let's just close down the new, should it be yes? Yeah, it should. We need to store the return value. Let's not do an if statement right away, and instead we set the S2 to this, and if S2 is less than 0, then we close. Yes, then we don't need to close it, because it's not really open, but we need to do something. We will just return. So we go to the next iteration of this loop, right? Perhaps we should do some kind of sleep before that. Let's just do sleep 1. Is that sensible? We're accepting connections. We can try it this way first. Okay, so if this doesn't go wrong, we will have a connection. And we need to obtain the address fields. So how do we do that in an easy enough kind of way? The port should be rather simple, right? So S or port equals H ton S. Is it S ton H in the different direction? Let's check the man page. So man 3 S ton H. No, H ton S. Or wait a minute, we are changing 2 bytes. So if we have FF05, for example, the first time around we change it to 05FF. If we run the same function again, we should go back to where we started, right? Let's try that. Oh no, let's shut down the wrong window again. Let's see, we were in cache 22, export home equals pwd. No, export, oh, like so. And then we go here, and let's just do, so we want it to be an int16 return value, and we're going to run H ton S on a int, I would think, of the client structure, and we want the SYN port. Think this should be right. And then we will need to obtain the IP address. That will not be as simple, I think. HOS, no. Here we need some kind of library call. So let's see. One way it's inet address. The other way should return a char. This one does. It's deprecated, but I think I'm gonna cheat a little and use it even though it is deprecated. And perhaps we can fix that later on. So struct in address in. Okay, it just needs that part. Okay. So, and what was the name of the function? inet n2oa. Okay. So the IP will be inet ntoa of the client's S address, right? And then we will just print out connection from SD, and we will do IP and port. Let's do this to begin with. And return. And let's just check the chat for a little bit. John Papa says, my favorite programmer. Thank you so much, John Papa. Welcome to the stream. And let's see. Let's compile this thing, right? Oh, where did we do a mistake? Pointer targets in passing. Argument 3 of accept differ in signedness. Alright, it will not accept an unsigned. Alright. And what did we have? Len, int len. So if we do unsigned int len, perhaps we can even do int 32 len and cast it to int something like this, making use of our own data structures, right? Okay, that's better. What does it say? Invalid type argument of star. Perhaps it should be dot, because it's not a pointer type. So try dot. You use a pointer, you use an arrow if it's a pointer, if CLI is a pointer, and you use a dot if it's a regular structure, right? So let's do space and clear and make, and now there's only one thing left. Struct address in has no, okay, we need to cast that, I suppose. inet ntoa CLI s address. It has no member. S CLI s, okay. Struct in address, perhaps, and it should probably be a pointer as well. Or let's try it this way first. Yeah, that is actually a good enough error message. It has no member S address. Did you mean SYN address? Yes, I did. That's why it doesn't work. Sometimes GCC actually gets it. So let's just do that. CLI SYN address. The address of all SYNs. Here, make, boom. There we got it. And if we run this thing, it starts up. Very nice. And if we telnet to it, 127.0.0.1, and now my cat is soon everywhere on my keyboard. And telnet 127.0.0.1, and we use the port 120.49, and now it should probably connect, but it should... 1 second, I need to remove the cat. Du måste vara snabbare med. Sorry for the interruption. My cat can be quite eager sometime. So let's see what happens. Okay, it opens, it connects. And how does our program look? Connection from 127.0.0.1, and this port is the client port, by the way, the other side of the connection, so it's not wrong, probably not. Let's do a netstat an, and we grep for string colon 120. What was it? Let's paste this instead. Okay, so this is our connection. This is the server side, 120.49, and this is the client side. And then we have the other direction as well. So this port is right. Everything is working perfectly this far. And now everything is great. Alright, so we can accept connections, you guys. Let's close this down. So the next step is to, let's see, how do you do this on a Mac? It's always funky to find. There we go. So, alright. Now we have successfully accepted the connection and recovered their IP and port information. Let's create an instance of our own data type and fill it out. So what we need is a client, and we will simply do it here. So client equals a client star of malloc with a size of struct s client, like so. And if we are not able to allocate for that, that's probably a very big error, so I think I will do assert client. Actually, we can discuss that later if we need to choose a better solution. Alright, so now we have constructed that thing. Inside of that we will have an s will be equal to our s, and this time we should have the arrow here, because client is a pointer. And did I create the variable? Oh no. Then we have a port field. So client port equals port.
And my cat is here again. You can't be here, cat. Sorry. I'm really sorry, but that's not possible. Sorry for the interruption. It's very annoying, and if I close the door, he will stand out of the door and bang against it and meow. So that's not really a solution. I have put my brother to try to be a guard of the cat, but it's quite difficult. Anyhow, let's go back to this. I have copied our port to our structure, and then I will copy the string with string copy. So we will have a client IP. We'll copy the IP, and we will set the maximum to, how big is it? 16. So let's do 15 now. And let's actually zero this whole structure first. So 0, and it's a client and it's a size of struct s client, and then we will need to create that function. So it's a void 0. It will take an int 8 buff and a int 16 size. We'll need an int 8 p, and we will need an int 16 n for n equals 0, p equals buff, and we will loop as long as let's see, as n is less than size, and each iteration we will increase n, and we will increase p, and that will be almost it. And then we will do like this. So p equals 0. Yeah. So this will zero basically any structure. Before we forget, let's put it here to have a little bit order. Void 0, int 8 star, and int 16. And perhaps we need to, let's see, no, we don't need to cast size of, it'll figure out on its own. So if we copy the maximum to this string, we still have a 0 at the end because of this, right? Alright, so what will we do now? This is the main loop. So we will do something. We will fork, right? So we need also a PID. It's a PID T. PID. And what is forking? Well, you take the current process and you fork it. So you split it in half, and your program continues in 2 independent parts. So we can run things concurrently. So we'll simply do n PID equals fork, and this is quite simple actually. If
we have a PID. Then we are in the parent. So what will we do here? Not much at the moment. Let's just return. So we go to the next iteration of this main loop. Perhaps we will add some other stuff here. We can clean up a little bit though. Right. So we can free the client. Let's leave it at that. And well, if PID returns 0, what does that mean? That means we are inside of the child. So then we will run the child loop. And what will we send to the child loop? Well, the client, right? And how will we loop this thing? Well, same as we did down here with the server's main loop. We looped as long as the continuation variable is true. So let's create another continuation. This time we call it the child continuation. And where are we? Right here. So basically we set the child continuation to true, which means that we should continue looping. And then we will just do while C continuation child loop. Simple as that. And when child loop is finished, we will close the S2. That's a socket. We will free the child structure, the client structure, and we will return 0. Okay, something like this. So we should be able to test this right. Let's also just temporarily before this, or maybe not temporarily actually, let's just print dprintf is like regular printf, but it sends to a file descriptor, so it can be either an open file or a socket or something like that. So S2, we might optimize away these kind of functions later on, but right now it's good to have. So let's just do something like 100 connected to cache 22 server. And we will also, let's do dprintf s2, yeah, something like that. And the child loop this far will not be much, so let's just do void child loop client and sleep one return, just temporarily. And let's add this as well.
So void child loop, and we will send a pointer to a client structure like so. Alright, let's see if it compiles. We missed something, probably a typecast or similar. Passing argument 1 of 0 from incompatible pointer type. Client. Okay, we typecasted this a little bit weird. Where is it? Here. It should be int 8, right? Because that's the format we want it in. So we can parse one byte at a time. Okay, that's better. Implicit declaration of child loop. Okay, I used those annoying underscore thingies. There we are. Remove that. And it's still as readable, right? Readability is a very subjective thing. And return 0 from a void, that's right. Where was that? Child loop. Return 0. Is it this 0? Yeah, probably is. And make. There we go. Okay, let's start this thing up. And did we have the other window? We don't anymore. Let's tell it to localhost on port 120.49. Connected to server. This is being sent by our server. So we are having a connection, ladies and gentlemen. Let me just check out if I missed anything in the chat meanwhile. Here we go. Oh, you've been busy. So let's see. When will it close? I answered that. Is stream over? No, it's most definitely is not. Internet connection was cut off. Nice. Arnhem, close. Problem with my internet. Uh, 200 is server okay, that's correct, but this is not really a server okay. A 200 should be sent by the server when the client has sent something. Like in a web page, you request a web page, you get 200 okay. 100, I think, if I remember correctly, is more of informational stuff, such as you are connected to this server. I might be wrong though. Anyhow, we are defining this protocol, right? We together, so we can make up anything we would like. Actually, I just did a number thingy to make it more understandable, so to speak. Okay. Any questions this far? Please go ahead and ask. Are you back with us, Angel? Great, Arnav. Great, Angel. If you can hear me now, I would like you to choose a moderator, because you are being promoted to the chief moderator, and you will have up to 2 sub-moderators that will help you with the job. So you can do that while I continue a little bit further. It's like 5 minutes left of the stream. Perhaps we should... Yeah, let's just do this, because I said 3 hours and I want to keep the times, okay? So, however, we will have a stream very soon, perhaps even next Friday, where we continue this project, because this is a big project. It will take multiple streams before we are done, and meanwhile, in the middle of these streams, I will still give out a regular video every like 4 days or so. So in those we are currently working on the binary tree, and then we will merge the binary tree implementation with our database server implementation, getting a real good, hopefully faster than Redis in-memory database. Sounds kind of cool, right? Okay, Arnav. I will, however, create a recording, and I am creating a recording of this stream. I will just need to do some post-production so it's up to the standards of my channel, but I will release it some time tomorrow, okay? And I will do an announcement on the on the community, right? Thank you, Angel. But before we end, we have a couple of minutes left, 5 or so. If you have any other questions about programming in general, doesn't really matter which language, please feel free to ask them. I will try to answer as much as I can. Okay, that's very interesting, Arnab. The thing about the process.age. If you want to, you could send me the code when you are done, and I can tell the rest of the rest of the subscribers how to fix it on Windows, if you want to. If so, you can write to me in the comments or something. Okay, but thank you, Angel. If you guys don't have any additional questions, I will thank you for showing up. I hope I see you next Friday as well. And take care, everyone. You know I love you guys.
Okay, we are live. Welcome everybody to yet another stream of mine. This is my third. Let me just verify that everything is working as it should be. Can you hear the sound okay? If so, please write in the chat. Can you hear me okay? Okay. Thank you, Arnav. And hello, Ansul. Welcome to the stream. For you who don't know, Arnab is my dear moderator. So he'll be looking after the chat today. We will soon be starting with the actual coding. I will only take a couple of minutes to talk to you guys a little bit and let other people join as well, because there's always a couple of latecomers, so I don't want to start coding right away and they will possibly miss the first part. Hello, Angel. How are you, my friend? And hello, Hezekiah. I'm sorry about the pronunciation. Okay, hello, Mr. 21. Yes, and we are not just doing Redis, we are coding our own Redis. And hopefully it'll be faster than Redis. So I can take... and hello, Imoras. Welcome to the stream. I can take a little bit of... I can tell you a little bit of information about the project that we are going to do. So let me show you what I stumbled upon. I was checking out the Redis. For you who don't know, Redis is an in-memory cache database. Probably the most used in-cache database in the world. So I went on to this web page and I found something. Let's see, this one. Get the world's fastest in-memory database from the ones who built it. And I thought to myself, well, what if we can do better? What if we can build the fastest in-memory database in the world and force Redis to change their homepage and write something like, get the world's second fastest in-memory database? Wouldn't that be kinda nice, everyone? So that's a general idea. And my thought is we're gonna build this on a binary tree, and we're gonna optimize it using our own implementation of a hash table. So that's basically what we're going to do today. We have, I think a lot of you have seen that episode where we build a binary tree. So we will finish that binary tree and integrate it into our database, and then we will try to optimize it, and we will do some testing to see how many collisions and stuff. I will talk more about how that works a little bit later. Let's see. Hello, Coffee. Welcome to the stream. And hello, Zuzu. That's right, Coffee. We have a new moderator.
And so yeah, that's basically the general idea. And I think we should get started. I'm planning to do about 3 hours, but we will have a 20-minute break somewhere in the middle. So that's basically it. Sounds good, 21B. And hello, Dheeraj. Ready? Good that you're not missing this stream, and welcome to this stream. I hope you will find it interesting. I think the topic is very good today, and I think we can do something really interesting with it. Anyhow, I will move over this chat for a little bit, and I need to log in to my system, my dear Code Planet server. So let's see, let's do a new screen. And for those of you who don't know what screen is, it's one of my favorite Linux programs actually. It makes it possible for me to I can do like create a window like this and toggle between really fast with a key combination, and if I get disconnected from the server, it will look exactly the same when I reconnect. So the screen is alive when I'm not logged in. And screen is a standard tool in almost every Linux distribution. Yes, so let's see. There are two projects. So we have this. Let's see. We have the tree. This is the binary tree. Let me just show you a little bit about it. We are going to code in VS Code today, but I can show you faster in Vim. So let's see. So this is what we have done this far with the tree implementation. Basically, we have two different kinds of structures. We have nodes, which connect to other parts of the tree, and we have the leaves, which contains the actual data. So every node becomes a level or a folder, so to speak. So basically, we can have like the root as the first one, and then maybe we have one folder for the users, and then we can have a lot of the leaves inside of these folders. So we can have like users and login or something like that. And the general thought is that when we search in the optimized version of the algorithm or whatever we should call it, then it should be able to find stuff in every folder without having to go through the entire structure every time. So that's the idea. And there's only a couple of functions in this. We have a zero function that just puts 0 in a variable or part of the memory. We have a create node, which creates a node, so a folder. We have a function for find last, and when I do these kinds of functions, I usually call it something like find last, and then I add a suffix. So this is the linear version, and later, and I use like an alias
a macro which called just find last. So from the beginning I point that to this function, but then when I create a more optimized version, then I can just point the alias, and I won't have to alter a lot of different parts of the code when I want to use the other function. And then we can create a leaf with this one, and then we have the main. And we will not have any main in this part of the code when we are done, because this is going to be more like a library. But it's good to have this when we are experimenting and double checking that everything works and so. So this is the tree implementation. We're gonna keep building a little bit on that. And then we have the actual server. It's called Cache22. So this is where all the server stuff happens, the network connection and all that. So what we did last time is we set up all the different networking stuff. So we prepare it to listen for a TCP port, and when we do get a connection, it will let's see what we did. Yeah, it will fork and create a new subprocess, and that subprocess will run this looping function, which doesn't do much at the moment, but we will put so it will listen to the commands that we send to the server. So this is a lot of boilerplate stuff mostly at the moment, but my hope is that we will finish this part of the program today, and we will have at least a linear implementation of the search algorithm, and possibly more than that. And I will do another stream if well, I will do another stream anyhow, but it will probably be one more session with this project. And for you who well, those who's not listening today and it's not here watching live, will get a second chance when I publish the recording on Sunday. And I will also create a reference file. So if we do go to any web pages where we get any information or stuff like that, I can write down the link, and afterwards I will put this in the description of the recording when I release it. So that's basically what we are going to do today. So what do you think about that chat? Do you think it will be an interesting project, perhaps? Great. All right then, let's get started. So I will, as usual, go into this and set my home directory to this directory, so it's a little bit easier to handle. And it's not only because I want to have a small prompt. It's also if we have like a couple of subdirectories,
like this, and maybe one more even, like this, and I go in there and I do stuff, then I can just do CD to get back, and it will not fill the entire screen every time because of the path being too long. So it's quite nifty. Alright, I will start by copying over the tree implementation to this directory. So I will do something like this. I will go to the tree and I will copy star dot. I want the C files and the H files, and I want them in here. So there we go. I will also need to update the make file, but let's do that part inside of VS Code instead. So I will go into my Sociopath client and find my cache 22 folder, and then I will just open it in editor. And perhaps I should include that link to this program as well, in case you are also like me coding on an external Linux virtual private server or similar. So let me just see, it's www.birch.com and Sociopath. So this is the page, and it works for Mac and it works for Windows. So I will save this link and put it inside of this reference. So Sociopath SCP client remote edit your code like so, and let's see where my VS Code went. I need to make it a little bit smaller so it should fit on the screen. Something like, I think we can do like this actually. Like so. I hope the text is big enough for you. On small screens it might be problematic sometimes. Alright, so let's open all of these files. And didn't get the make file, so let's do like this. The reason it didn't get the make file, by the way, is because you configure the SCP client by telling it what kind of file extensions you want to use. So I have configured it for .h files and .c files, etc., but not for the make file, so that's why. But that's easy to fix. You just edit the configuration file. It's quite self-explanatory. Alright, so we need to add the tree implementation as well. So what do we have? We have a tree, or we want a tree.o, and it's coming from tree.c. We want to run cc with our flags, and then we will have the -c and the source file. So this is for the source file. When we have an O file, we can compile the actual tree binary, and we need the tree.o as a dependency, and then we will run cc with our flags, and we will have the source file -o and the target, and possibly some LD flags as well for the linking. And we'll do clean catch22, let's do tree in between here, like so. And so now I should be able to do make tree. Okay, it didn't really like my spaces instead of tabs, probably due to the copy pasting from the terminal. So let's see. Let's do all of these. And this one as well as this. Okay. So let's try it again. Make tree. Yes, it compiled. And here we have our tree. So we haven't yet coded a function to display the tree. So what we are displaying at the moment is a value from one of the leaves, and the addresses of, I think it is the leaf and the node, if I remember correctly. But everything works this far. And by the way, if you have any questions, I will not be able to see it in the chat when I am coding, but Arnab will take care of the questions, but save them, so when I ask him later on, are there any questions, he can give me one at a time. So he's keeping track of all the questions. Great. So let's see where we will start. Let's also compile the rest, by the way, so we see that everything is still working and I haven't been editing any stuff. So as you can see, it is listening on this port number 12049, and the actual port number was decided by you guys last time, but you can specify the port. I think we did it like this, right? Yeah, you can specify it directly on the command line, and you can also just edit a constant definition inside of the H file. Okay, so everything is up and running, and let me show you what happens when you connect as well. So if I just run telnet, which is a standard tool in Linux for connecting to TCP servers, very good for debugging. And let me just do one more thing. I usually do something like this, because sometimes I close down the window, and if I close down the last window, then the screen process terminates. So I usually do some bash script like this, so I always have one window which I don't touch and which will not be closed down. Okay, so let's see, the port is 2343, And as you can see, we are connected to the server and graded by this 100 connected to the cache 22 server. And these kind of server codes, I'm not really sure if we are going to use it like that, but let's keep it for now. Alright. Let me just cough. Sorry. Okay, so where to go next? I need to have some functions that take care of the input from the user. So let's begin there. I want to be able to break down these commands into different space separated variables, basically. So let's see, we are running the main loop and then we are running the child loop as soon as we get a connection. So this is all that we have this far. And we are passing this structure around to the different functions. And if we take a look in the H file, the client structure looks like this. So we have the socket, the file descriptor, which represents the connection. And then we have the IP address in regular format, like this kind of format, as a string. And then we have an int16 for keeping the port number. So that is what we are passing around. So what will we do here? We want to grab the input from the user every time this loop iterates. So let's create a string variable, or int8 as I use in this project, and let's call this buff and 256 as size. So this will be the buffer that we read from the socket file descriptor. So let's start there. In order to read from a file descriptor, we use the read system call. And before that, by the way, I want to zero out this variable, like so. And the first argument of read is the file descriptor, which we keep inside of this client structure, and S, I think we called it. And then we read it into buff. And finally, we need to specify the maximum number of bytes to read. And I usually take one less than the size of this variable. Okay, so now we have a command, and the command will look something like this. Select and then the path, so like users, and then we specify the actual leaf. So something like if we have a folder for the users, we might have a leaf for the different usernames. So this can be one command, and then we will have commands like create, just to create one of these nodes, like this. And in order to grab the data, we use select for that, right? But in order to alter and add data, we use insert, and we specify the path like this, and then we will just put the value right here without any quotes or anything. So basically what I want to do is I want to have a function, or several functions actually, but I want to break it down so we get this command inside of one variable. We get this possible second token in a different variable, and then this third in the third variable, and then we will call that specific function based on this command. So basically we will have a structure which looks something like I don't know what to call it yet, but let's say ABC, and then we will have a function pointer as the first argument. So let's say we have a function for the select, and then we have a string for it as well. So the function we are going to write will map this to a specific function and run it and send all these as arguments. Then it will be very easy to add these commands, and it will also be very easy in the future to be able to create plugins and more functionality. Alright, so let's see how we are going to do this. I think we can do it right inside of this child loop. So how do we separate it in these kinds of tokens? I don't want to use any library calls or similar, so let's code this ourselves. So basically we will set this let's create a by the way, before I forget, the read function will probably need a casting for this one. No, not indate. It should be a char when we call this function. This one is okay, and this one is okay. Alright, so let's create a char pointer. This int 8 is actually a char. It's an 8-bit integer. So let's see. We will do something like, I think a for loop would be the easiest. So in the beginning we will set p equal to buff, and we will loop as long as, and then we will have a couple of conditions right here, and every iteration we will just increase this pointer by 1. Okay, so what are the different conditions? Well, we want p to be, or the thing that p is pointing to, we want it to be non-zero, right? Because when we reach the 0, we will well, the string will be done, so to speak. And we also need to keep track that we don't overflow this if they send a very long command.
we are limiting it with this one, but I would feel more comfortable if we had a counter as well. So let's see, we can set this to the int16 version of string length, and we pass the char version of buff. So there's a lot of these typecasts because I decided to use this standard, but it's not too troublesome, because if we forget, the compiler will yell at us. Okay, so let's see. N contains the number of characters, and perhaps we should do something like, if n is bigger than 254, we set n to 254. So we are using both the we are using two different ways of protecting ourselves. Okay, so let's say we decrement the n each iteration, which means that n should be positive. And let's do like this. So what else? We should also stop if I think we put it like this. We will also stop if p is equal to the space, because remember, this is how it looks. So we will go character by character until we find a space, or until we are at the end of this string. We can also check for p equal to new line, and perhaps we should check for these annoying Windows style new lines as well, or carriage returns or whatever. Let's see. Okay, so p equals buff. We check that p is positive, that n is positive, and that p is not this or this or this. So basically, when this loop is done, we don't even need a body for it actually. When this is done, we have a couple of different scenarios. Either p is equal to 0, and what do we do then? That means that the command, let's see, it means that the command is filling out the whole buffer. So we have sent something like just insert. Let's create a couple of variables to hold the results as well. So we will have a command, and we will have a folder, which is the second argument, and then we will possibly have additional arguments. Okay, so when we reach this stage, we can set the command equal to buff, because that's the only thing that we have inside of buff. And what else? If it's equal to space, then we will need to copy this. So the easiest way is to take this space and replace it with a 0 byte, because then we can just do a string copy on the buff in order to get the thing we want. So let's set p equal to 0, and then we will need we need an additional buffer. So maybe we shouldn't use pointers for these ones. Let's do this instead. 2, 5, 6. 2, 5, 6. 2, 5, 6. Like so. Or maybe, let's see. Well, let's do this for now. So in case, let's change this so we don't forget. So in this case we want to copy, and we want to copy into the char version of CMD, and we will copy the char version of buff, and the maximum number of characters is 255. And before we do that, we will also 0 out. Let's do that before the conditionals, by the way. So let's 0 out CMD 256. Let's 0 out folder 256, and let's 0 out args 256. Like so, and now my cat will try to intrude. Never mind. Okay, so we have zeroed out the variables. We have copied the command in case of when we have issued just the command. And in this case, we will set this to 0, and then we will do the same as here. We'll copy to the folder from the buff maximum 255. Yeah. And then we are done. We also need to sanitize these by removing those new lines and stuff. Perhaps we should have done that from the beginning, but let's hold off on that for a little bit. Okay, so we have our two conditions. We also need to, well, basically we can do the same as here when we encounter one of the new lines, right? We want to overwrite it with a 0 and then copy the stuff before that. So let's make this if statement a little bit bigger. So if p equals this, and if p equals this,
And finally, if p equals this. Okay, so we kill 3 birds with 1 stone. Right. Let's put it there instead. Okay. So, is there anything else we need to consider? Yeah, this one. When this reaches 0, it should be treated the same way as this first condition. So if p is equal to 0, or if n is equal to 0, then we should do this, right? If p, this should be an or, because it's equal to this, or this, then we do this. Okay, good. Okay, so now we have the command. Now we want to continue by doing the same again. Basically, we will simply loop over in the same way. So it will be a little bit undry at this stage, but it's better to just make it work, and then we can use time to make it more good looking code if we want to. So let's just completely shamelessly copy paste this and just alter a couple of things. So we will not zero out these structures again. Okay, so p will be equal to what actually? What is p equal to at the moment? It is pointing at this, right? The space. Or it is at the end. Let's go to sometimes those kind of solutions are the best to start with, at least. So if this happens, then we are done and we can go to done. Else we do this, and then we continue along with the second iteration. Okay, so then we can set buff. We can almost leave p as it is. We only need to increase it by 1. Let me have one of these. Let's copy them all, so I have them available. It's easier to grasp how the things will look. So currently we have the p pointing towards this space, and we want it to start by pointing right here. So we increase it by 1, and then we do a loop again, and we check if we should reset the n too, right? How should we do with the n? No, we can leave it as it is, I think. Let's do that for now. Okay, so we check if p is not 0, if p is not space, if p is not this or this. Right. And then we do this check again. only this time we will copy to not the CMD but into the folder. And by the way, this shouldn't be folder, this should be command. Am I right? I think I'm right. Okay, so we copy it into the folder, but we can't copy the entirety of buff any longer. We need to have a pointer instead. Let's name this F, because it will point towards the folder's beginning. So P equals buff. Let's see, which one is it? Here. So P++ and then F equals P. So basically the F is pointing towards the beginning of this second argument, which means when we do the actual copying, we will be copying it from F as a starting point with buff. And same here, F, like so. And we'll also have the go to done. And then all we are left with is the last argument. So let's see, in this case we have spaces and stuff. And we copy into folder from F. So let me see. So we start here and then we copy this stuff. So P is pointing towards this, either this or P is pointing toward the end of the string or of the buffer. So if we are pointing towards the end, we should have jumped to done, right? No, we do a check. Yeah, we do it here. So the only thing we will need to consider, let's see, here it is. The only thing we need to consider is that we are here, and if we jump one more step to the right, we should just be able to copy the end of this, basically. Am I thinking correctly? We copy the folder, and in here we are. Well, let's try it out. It's a very big function with a lot of moving parts, so it's a little bit tricky to keep track of everything. We'll probably have to troubleshoot a little bit, but when we create all of these kinds of functions ourselves, we have a much greater possibility to optimize it. If we just use something off the shelf, we don't. So I think this is necessary if we're going to beat Redis. Alright, let's increase P and if P is positive, what will we do? Then we will do a string copy into the char version of args. And what do we want to copy? We want to copy the char version of P. And what will be the maximum? Well, we can still use 255 since this is a different string variable. Why is this here? Okay, so now this contains the arguments, and possibly it also contains the new lines and stuff. So let's deal with that now. So if P is positive, then we do this copying. Then we can point P towards our args. We can do it like this. We set P to args and we loop as long as P is positive. As long as P is positive, and P is not equal to a new line, and as long as P is not equal to this. Let me just check this first one so I didn't mix up the logic. If P is positive and N is positive and P is not equal to, because we're going to stop the loop, right? So else if P is equal to this, or this, or this, and then it'll be the same right here, because P should be positive, this should be positive, and this and this and this should not be any of those, like so. If P and N are, if P or N are negative, we do that. Else if yes. Okay, that looks right. And now P equals to args. We will loop as long as P is positive and P is like so. And what will we do each iteration? We will simply do P plus plus. Like so. And then we can just set P to 0, right? Because if it's already 0, this won't mess up anything. And if it's one of those, we want them to be 0. So this should fix our new line problem, I think. Okay, so now we have our variables. Let's print them out one by one and see if, let's actually print them to the user connecting with the client. So we will print
command. Like this. And this is the command. And this is the folder. And this is the potential arguments. I have a feeling that we have missed something and this is gonna segfault so badly, but well, there's only one way to find out. So then we can return. Okay, well, let's see what happens. And I have been disconnected. So I basically just use screen -RUD, and then I have a couple of different screens. If I only have one, I don't need to specify this number, but now I need that. So 14 is the one, right? Yeah. Let's see what happens. Okay, not as much errors as I anticipated. Oh, the ABC, I never removed that. So let's go to this one. And then I space down a little bit before I clear the screen. And why do I do that? Because when I compile and get a lot of errors, then I want to be able to scroll up and easily find the beginning of this command. Okay, what does it say? Okay. Where was that? So this looks weird. And this same problem here. But I did see something else. What was it? A colon there. 82. 82. There. It should look like this, right? Basically, when you end a for loop or similar commands with a semicolon, then it basically means that you don't want to have a body to that loop, because all I need for this is a different looping, so to speak. Loop until I get to the point I want to be, and then I do this once. Alright, let's try again. Oh, we get more errors, not less. Well. Oh, it's a lot. Expected. Okay, this error is probably producing most of the other ones. 34. 34. This one. Okay, we have this condition and this condition and this and this.
and this. Okay, this should be here, right? So then we should probably do the same somewhere around here, and hopefully most of these errors will disappear. Yes, but still I did something similar. No, it's still complaining about 82. Still complaining about 82. It's my unlucky number 82. Let's see. Okay, so we have a for loop. Then we have a couple of conditions. Well, we don't really need these parentheses. So we check for this and this and this, and then we don't need that, but we do, however, need this, right? Let's try it again. Okay, now we're getting somewhere. Warning, this for clause does not guard this statement, but the latter is misleadingly indented. It's actually complaining about my indentations. That's quite funny, actually. So for p equals this, and we check that this is true, that this is true, and okay, I kind of agree with GCC. This should be there instead. It was quite sensible after all. And only one left. String copy output may be truncated. Oh, I dislike this error so much, or warning. Because I have knowledge about my variables. And I don't think that GCC should annoy me about that. Let's actually remove this one. I always forget how to do that. Let's see. Need to go into my OOP. No. And I think I have something like this in my lambda code. Right, here it is. So let's go into our H file and somewhere at the top we put in this, and which error or warning rather do we want to suppress? This one, because it's not complaining or warning me that I am causing a buffer overflow. No.
it's complaining that I am not copying as much data as I should have. So it's the other way around, and I don't really care for that. So then we can add this pragma. And we need to pop as well, and let's do that inside of this C file at the bottom. There we go. And then we do the make clean, and now we should hopefully don't get that annoying error. Great. Okay, let's try this. Do you think it will work on the first try? Let's see. So I will connect to localhost, and what port did we use? 12049. 12049. Here we go. And let's say we will run the command create users. Did we cause a loop perhaps? It's not crashing it. Oh, wrong window. Okay, so how do we debug this one? I think we can start by doing an ltrace that follows forks. This will show us all the library calls. So let's telnet into this and issue the same command as before. Probably we won't see much if the actual looping is causing this. Let's see. dprintf broken pipe, child exited. Looks like it did crash after all. It runs the string length on nothing. Why on nothing? We read without return. We have a dprintf. This is probably the welcome message, I would think. But it's writing towards 4 here. And here it's writing to 3. Okay. Let's look through the code a little bit. Where were we? Right, child loop, client CLI, and we zero out the buff. We read from this file descriptor into the buff with this size, and n equals the int16 value of string length on the buff. This should be okay.
I would think so. Perhaps there's something wrong with this structure. What if we would just try to print something there? So if we do write client S, and the new line, and this would be 4 bytes. And then we will exit 0. So let's compile it again, and we can run it the usual way first. Let's connect, and we type something, and we do not get a response. We do not get a response. So, did we do something wrong with that? With that client structure. So let's see. This is inside of the main loop. We accept the connection. We figure out the port and the IP. What then? We allocate the client structure, size of struct as client with 0. Everything. We set the S to S. And what is S? S is S2 we get from accept. That is the child's file descriptor. But the S, that is the main process. So that's probably it then. Let's save this. And well, it's not the only thing actually, because we shouldn't crash, but at least we're one step closer. Let's remove this for now. And let's compile. Where are we? Is this the wrong? Yeah, it's the wrong window. There we are. So let's connect to this one, and let's issue the command create/users. Okay, so the command is create, the folder is users, and the argument's empty. Beautiful. And what happens if we issue only something like help? The command, it's still help, but there's a new line with a folder. Okay, we need to remember that. And if we do a longer command, so insert users this, and then some kind of value. Let's add some Shakespeare to the mix. So the command is insert, the folder is this, and the arguments are those. That's how it's done, ladies and gentlemen. Now I think is an excellent time for the break. We are halfway through, and yeah, let's do the break now, and let's return in 20 minutes. See you then.
Okay, everybody, we are back. Yes, Arnab, let's take a couple of questions. Would you select one? I haven't been following the chat because of the coding, so you can pick one. Well, the best way to learn, I think, in order to really learn, so you become really good at coding, you need to create a project of your own, and it needs to be a project which matters to you. So let's say you are interested in football, for example. Perhaps you choose to create like a program or like a game where you manage a football team. Or if you are interested in video games, perhaps you could create some kind of an editor or some kind of calculator which helps you to plan your armies in more effective ways. Or because if you combine the coding with an interest of yours, then you will be passionate about that project and you will learn double the amount you would have otherwise. Because I tried to learn programming a couple of times, and I learned a couple of commands and stuff, and I did a couple of examples, but it never turned out to anything. But then I combined it with other things, and I created projects that really mattered to me, and then it was a whole different subject. So that is my I don't know, my idea when it comes to that kind of stuff. Let's see. Should we not close the copies of socket file descriptors that the child process receives in the child loop? No, we should not close it in the child loop, because the child loop runs once every time we get a command, and during a connection you should be able to issue multiple commands, right? So let me show you what I mean when we actually should close the socket. Because if we look at this code in the main loop, so here is a fork. So this is where the child process begins. And what do we do in it? Well, we print out this welcome message. We set the variable continuation to true, and then we loop, the child loop. And as long as continuation is true, we keep reading commands from the user. When a continuation is set to false, like when the user issues the quit command or something like that, then we break out the loop and then we close the socket, right? Alright.
Do you have any additional questions? No, the code is currently not available on any repo like that. It's like this actually. I always want all my videos to be free and for all to access, but I still have to earn a living. So what I plan to do is create a premium feature where you can donate because you like the video in question, and if you do, you do get a lot of perks. So you get like access to code, and you get a lot of different other things. So that is my basic thoughts on that. I hope you think that is okay. I am currently developing a website. Perhaps I can show a part of it to you so you see what I mean. I don't want to show the link though, because it's not done right. Let's see. So I'm in the middle of developing. It might not look exactly like this when I'm done. Okay, let's reload. So basically it will be something like this. The videos will be free and available on YouTube as usual. But if you watch a specific video and you think it's a good video, it's a video that you think is worth paying for, and you learn something from that video, then you can voluntarily go into this page and you can donate like $19 for that specific episode. And when you do, you get access to the code and stuff like that. I have a couple of different things as well planned, and we will also have a high score list with the biggest donators and stuff like that. So that is what I plan on doing. And do we have any more? Any more questions? Hello, Triumph. Okay. But I haven't released that website yet. I'm still in the middle of the developing. But if you do want to contribute, there is a way. You can become a member. And that is actually live right now. You see that little blue star by the name of Arnab? That means that he is a paying member. And then you get a lot of perks as well. So if you watch a video or you go into my main page, then you can click on the Become a Member tab. Hello, Big Master. Welcome to the stream. I can show you real quick that as well. So if we go into my main page, youtube.com, and then it's @ and Dr. Jonas Birch. So there, become a member, and I have it in Swedish, so that's why it looks different. But if you click that, then you will see the different levels and what you get access to for the different things. But it's basically not. Its focus is that you can contribute if you like to. So that's the main idea, and then you get some additional perks as well. But I think the main thing should be that you contribute because you want to, because you like the material and so forth. Angel is around, I think. I saw him in the chat before. Yeah, he was present earlier. However, we decided to part ways. He's no longer moderator, but we are on good terms. So hello, DevBytes. Welcome to the stream. There you are, Angel. Hello, my friend. And hello, Maglintala. Welcome to the stream. Probably didn't pronounce your name correctly, but you have to forgive me. And hello to Rajesh as well. Welcome to the stream. A time machine. Well, we could probably create a tool like the Apple time machine, but an actual time machine? Well, let's put it like this. If humanity ever figures out how to code a time machine, it will most definitely be written in C. Alright, enough of the questions. If you have any additional questions, or if you come to think about anything while I'm coding, just ask them in the chat, and we will. I will answer them when we pause the coding. I'll try to be better to check out the chat every now and then. Well, Arnav, there is most definitely a craze for C++ and Rust, but I still don't think a time machine will be written in C++. We need a language like C for that kind of. Well, C put us on the moon, right? And If we would have tried doing the same thing in C++, it would probably have crashed halfway to the moon. I'm just kidding. C++ is a wonderful language as well. Alright, let's continue with the code, shall we? So, we are able to handle the user inputs with some small bugs. We still haven't fixed the new line problem, and I need to reconnect. And 14, I think. Right. Because where was it? Some command that we issued had problem with a new line. Which was it? Help folder args. Let's check the code. Because we did check and alter the new lines for the last argument, and I think we did the same for the first, but what about the second? So where does the second start? It's right here. So we point towards the space, and then we increase by 1, so we start here. Then we run through this. So let's say we get a new line right here. So then we break out of the loop, and this condition should not be valid, but this. One of these should hit, right? And what do? We just copy into folder from F. And where does P point at this point? It points towards the new line in the buffer. Now we do have a P equals 0. And we do have this here as well. And here we are inside of the args. I think I want to test this again though. Let's just connect to the server and issue a couple of commands. So first let's just do something like this. So it prints the help and it prints folder and a new line. Why does it print an extra new line on the folder when we just issue one command? Let's see. So we go through all of this and we copy to the command, and what happens then? Then we go to this next step. Perhaps we should just do an if check at this point. Something like if P let's see. So in this case we have gone through the first, and if P is negative, then we are done, right? And then all our other variables should just be empty, I think. Let's see if this changes anything. So if I issue the command of help, okay, now it looks better. And this space is right here, that's just a tab, so that's nothing to worry about. And if we issue two commands, so we do create and a folder, okay, now I messed that up instead. Okay, yeah, I can't go to done. Let's see, because P is pointing towards the buffer, and if any of these are true, we set P to 0, then we copy the command, and if P is 0, well, of course it is 0. Let's do P plus 1 instead, because I want to know if the buffer has ended, you know. This one. Alright. Let's do this and this. And we need to run the program. /22. And issue a command, help. Okay, we're back here again. So how are we going to check that there's no more command? Well, we can, let's see, if P is not equal to a space, then there's no more command, right? If P is not equal to a space, then we are done. Let's try that. Okay, that looks right. What if we were to try to create a folder? No, we messed it up again. this is equal to space, then we should go, and it's not, because P or N equals, okay, we do have this condition. And let's see. We copy the command. P is equal to this, or this, or this. Then what do we do? P is not equal to this. Well, it's no longer equal to that. Maybe we should break out this into two different things instead. So if we were to do another else if, where we check for these conditions, so if we encounter this new line stuff, what do we do? Then we set P equal to 0. We do the string copy. And then we are done, right? So this should be another else if. Oh, now my cat is on the keyboard. Come on, Alex, look. Sorry, he jumped onto the keyboard. Let's see. Where were we? Yeah, else if. Okay. What did I copy over this now? What did we check for? Space. It's just space left, right? So else if this is equal to space, okay, so if it's a space, this we can remove. We just put a 0 instead, and then we string copy this stuff. Okay, so now it should work, I think. Okay. All those brackets. Else if, and we have this, and we check for this or this. and then we have that. What is this? I must have accidentally copied over this code. So this if statement, and then we have this. Do we end this? Yes, we do. Okay, let's try this then. No? 48. What is this? If P, else if this, else if this, okay. There we go. So we issue the command help, and it works. We issue the command create users, and it works. And then we do the insert users and this data. Okay, now it looks the way I intended it to look. Good. So what's the next step then? We need to figure out which function to call. So let's create something in the H file which we'll call a, what should we call it? A function handler, command handler perhaps. And how should that look like? Well, it should be a structure containing, let's see, let's begin by defining the function pointer. So that has a rather weird syntax. I think it's like this. So we put the name right here, and then maybe you should put the return type before this. And then you add to it the signature, the different parameters of the function. And what parameters should we have? Well, it should basically be 3 8-bit pointers. So we should have int 8 star, int 8 star, int 8 star. So this is basically one for each argument. This is a command, this is a folder, and this is the arguments. And what shall we call this thing? This is a connect back. It's a let's just call them callback. Like so. And then we need a structure as well. So the structure we call a command handler. And we basically just need two different variables in here. We need an int8 pointer, which is the string representation of the command. So let's call this command, and then we will have the callback function. So I should only be able to do something like callback. Let's call this handler here. And I don't think I should include the star, since I have the one here. Like so, and then we create a type definition as well. So we type def struct s command handler, and we will call it command handler with capitalized letters, like so. And then we will just create a list basically. So let's do a struct, and no, not struct, we have a better name for it. Let's do command handler handlers. So then we will have a couple of these, one per command. Let's begin by just doing something like hello. And if they issue the command hello, then we will say hello back. So I think we perhaps need to typecast this into 8 star. And then we need a function as well. So let's say handle hello. I think this is the correct syntax. I don't use this very often. Alright, and let's create that function as well. So void, no, not void, it should return an int32, and it's handle hello. And by the way, perhaps we don't really need to include the command, because we only need that to find the right function, and that we have already done if we call the function, right? So the only thing we need to have as arguments is two things. It's the folder, and it's the possible third argument. No, we do need one more thing actually. Can you figure out what? One thing that we want to pass to every function basically. That's right. We need the, let's jump down a little bit. We need the client, right? If we don't have that, we'll not be able to respond and stuff. And let's update the signature as well. So we will have a client, and where does the client get? It's down here. We need to think about the order of things. So let's move this whole stuff so it's underneath here. Alright. So here we have the arguments, and then we can just, well, this is a temporary thing, so let's just do a dprintf on the socket file descriptor, where we reply back hello, and let's put the argument here as well. Then we return 0. Yeah, let's do that like this. Okay, so now we have a function. We need a helper function which basically looks through these different handlers and maps. So we give it the string representation, and we get back this address to the function. So that is the next step to do. That should be quite easy to write. So we will return a, let's see, what did we call that? A callback. And that is a pointer by definition, I think. So callback, and what should we name this? Let's just do get command, and we send an int 8 command. And we should just search through this thing. We need to make this this should be an array. Okay, so let's just iterate through that array. I'm just thinking we kind of need to know the size of that one. Let's do something temporary. Size of handlers. I think it might be possible to do that, right? So this is called get CMD. Where do we have our main? Here. So we run get CMD with something, hello, and we return 0. I just want to see what size of returns in this case. This one. Okay. Handle hello. What did I name it? Wasn't it handle hello? Let's see. Okay, I never wrote that function. Let's just do it signature then. So we will have an int32 handle hello, and it's gonna take a client, but didn't I write that function? Yeah, I did. Handle, okay, is it because it's below? Let's do a function declaration. So we have int32 handle hello with a client and an int8 star int8 star, like so. Okay, that disappeared. Format expects argument of type int, but argument 2 has type long int. Okay, it's long. All those 64-bit CPUs, right? So it should be CU, right? Let's put a new line as well. And we need to, where is it? 202. This should be an int8 star. Alright. So let's run this thing. 16. So we have this stuff and this stuff. What if we were to have 2 of those? Will it still calculate it correctly? So now we should get 32, right? Okay. Alright, so that makes things a lot easier actually. Otherwise we would have be forced to like have a define or something like that, which contains the number of well, number of things in that array. But now we can calculate it quite easily. So let's remove this. And what should this function do? Let's create a call back which we call CB, and let's do an int 16 of n, and then we do for n equals 0. Let's do it in 2 steps. Okay, so we have this and we need something, what should we call it? Array length. And array length should be size of handlers, and we should simply divide it by 16 then. This parenthesis is not necessary, it's just my own convention. So, and maybe we should do some kind of check first, like if size of handlers is less than 16, return 0. Okay, so we set n to 0, we iterate as long as 0 is less than r len n plus plus, and in each iteration we do a simple string compare of the char version of CMD and the char version of handlers and dot, and what did we call them? We have CMD and we have handler. So this should be CMD. So if those are equal, what do? Well, we do this. We set CB. Okay, we probably need those as well. We set CB equal to handlers and handler. And let's initialize it first. So CB equals 0, like this. And after this loop, we just check if CB is true. No, we don't even need to do that. If we just do return CB, it will return 0 if it is 0, so that's really not a problem. No, not cd handler. Call. What should it be? It should be a pointer, right? So x. And then we do it again. This time we don't get a match. Okay, let's try this. And then I think we need to call it a night actually. But let's make this work first. Alright, let's see. We'll recompile. Oh, what is this? We basically added to 3 lines of code or something. Indie handler has no member. Okay, that's just a typo. What is this? Probably all these errors originate from the same stupid thing. Let's see. Handler with a double H. Where is that? Handler, handler, handler. There. And we... Okay, I never finished this one. Okay, we need to break. So we don't search this unnecessarily. This is part of this. Okay, that explains all the errors. Okay, only 2 left. So what does it say? Assignment to blah 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 blah. Incompatible pointer type. So CB equals handlers and handler. And what kind of structure is handler then? Handler is a callback. Maybe we should put the star there after all. Okay, maybe we did it backwards. Let's remove the stars instead. Okay, now it's compiled. Great, let's run this thing. And it works accordingly. So first we do a check for hello. Does we have a function that can be discovered by that string? And yes, we found a match with this address. And then we tried to search for blah blah blah, and we got nil back, which is the same as 0 in Britain, perhaps. Alright, now my back is killing me a little bit, so I think this is good for one session, don't you think? We have managed to get a lot of work done, and everything has worked pretty well, I think. Yeah. Thank you, Arnav. And awesome job with the moderation and stuff. So we will do a new open for all free stream like this. I'm not sure when yet. It might be next Friday, but it could be the week after as well. We'll see. But thanks everyone for watching, and have a good day. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Sup guys, today we are gonna continue coding on our binary tree. We are going to create a pretty printer function which prints out the tree in a graphical kind of ASCII way. So it will be easier to understand how the tree is constructed, and it will also be easier to troubleshoot if we have to. Let's get to it. But first we need to add a couple of other things into our tree. So this is what we have this far when we run it. We create an example tree and we grab some values from it. And these are the addresses to the nodes. So what do we have this far? Well, we have a couple of functions. This is the first node, by the way, of the tree. It's statically defined and it's the root of the tree. Then we have the 0 function, which simply memsets to 0, a variable. And we have create node, which creates a node of our tree. So basically it will be like a folder containing the actual data structures. And here is a find the last leaf, and it's a linear version of it. And we do also have a function to create a leaf, and the leaves are containing the data. So every leaf will contain one string, basically, of any size. And that's basically what we have. And inside of the main we have a couple of example stuff, which will not be here when we are done with the code. So where do we begin? I think it will be useful to have a function which prints the tree. That will make it easier to grasp how everything is working, and it will also be easier to troubleshoot if we get into any errors. So that we will create, but before that I want to create all the function declarations, because I never did that previously. So let's just let's do it like this. So we have the 0. So void 0, and we have an int pointer and an int 16. So we have an int 8 pointer and an int 16, like so. And the next thing is create node, which will return a node. So we have our node, create node, and the arguments
we have a node as a parent, and we have a string as a path. So node like this, and an int pointer as a string, like so. Then we have the linear find last leaf, which will return a leaf pointer, find last linear, and we need a node, and finally we have this create leaf function, which does also return a leaf. So create leaf, and what do we give it? Here we do have a couple of arguments. We give it a parent and a string, so a node and an int 8 pointer, and then we have an int 8 pointer as the value, and finally we have an int 16 counter. So int 16 like this, and at the moment we do also have a main. Do we have arguments? No. Okay, let's see if we did this right and it still compiles. Yes. And the same results as before. Okay, so now we have a little bit better structure. So let's create this printing function. And in order to create that function, we need a couple of helper functions. One being an indentation function. So basically, we need to create a function which takes in an integer as an argument. So it will be called like this, indent, and let's say we provide it with the number 4. Then this should return a string with 1, 2, 3, 4 spaces. Or no, let's do it like this instead. Let's say we indent 2 steps, and each step being 2 spaces. So if we give it a 2, it will return 4 spaces. I think that's better. So let's begin by the function declaration so we don't forget it. So this will return an int 8 pointer, a string basically, and it's indent, and it takes in an int 8. Like so. So it'll be int 8, let's see, indent, int 16, what should we call this? Let's just call it n. So that's the number of indents. So how can we do this in a practical way? First of all, we need some kind of a buffer, which we will write to. So let's create an int8 buffer of size 256. So this we will fill with the data. We will probably also need a pointer. So let's start out by zeroing out this buffer, like so, and we need to have some kind of check to double check that this parameter is not too big or too small. So how big can it be, or should it be? We have 256 as a maximum amount, and each space is 2 spaces, which makes it 128. And then we will have a 0 byte at the end. So let's do the maximum for 120, just for the sake of it. So we can rely on assert in this case, because, well, as a programmer we shouldn't give a function bad arguments. So what do we assert? We assert that n needs to be bigger than 0, and that n needs to be less than 120. Right? So let's do a for loop. And we need some kind of counter as well, by the way. Let's call it I. So we begin by setting I to 0, and we set p equal to buff. So it points to the first part of the buffer. And we are gonna iterate as long as I is less than n. And each iteration what will we do? Well, for starters, we're gonna increase I by, by 1. And are we also going to increase p right here? Well, let's do that. So p plus equals 2. So we will jump 2 steps at a time. And at each step, we will simply string copy to the position of p. We need to do this. P. And what are we going to string copy into it? We will do the string of 2 spaces. Maximum 2. Like so. Let me just double check one thing. So we have, from the beginning we have nothing, then we string copy 2 into it, and then the pointer starts here, and we move 2 steps to the right, and then we string copy to this position, 2 spaces. I think this is correct. And at the end we will simply return the buff. but that buff is currently on the let me just remove this. The buffer is currently on the local stack of this function, so we can't really return it like this. We can malloc it, but the way I'm going to use this function is iterate a lot of times, so I don't want to have to free all these memory allocations. So let's do this as a static buffer instead. Static basically means that it will be accessible outside of this function, and it will keep its current content, but we will zero it out every time, so that shouldn't be a problem. Let's go to towards the end of this function inside the beginning of our main, and let's just try it out. So we will do a printf, and let's say we print something like int main, and a new line, and after that we put in an indentation and return 0, and ending bracket like this. And what will we send to this printf? We will do indent 2, and then we are going to, let's do like this and this and this, and let's call this something else, func, and this we will do, no, 1 here and 2 here, that'll be good. And then we will simply return 0. So this is a temporary thing, of course. And let's recompile. Oops, what did we do now? Conflicting types. Int 8, indent, int 8. Oh, I did an int 16. Well, we're not gonna be needing that many characters. Let's do this in int 8 instead, like so. And we jump down a little bit, we run make, and now what? String copy output truncated. Oh, I really do not like this annoying warning, because this is basically for people who don't have a clue how the memory works. Because this is a totally safe operation, and it's not even warning us that we can overflow the stuff. It's basically warning us that we might not overflow it. It's kind of bizarre, but I think I'm gonna remove these kinds of warnings actually. So let's see where I have that kind of code. So let's do cat of something like code OOP and lambda.h. Here we go. I never remember this pragma stuff. Perhaps I should not copy paste it. I should write it instead so I can remember it. So pragma gcc diagnostic ignored. I'll put it almost at the top of this H file. So pragma, what was it? GCC diagnostic ignored. So GCC diagnostic ignored, right? Weird English. And this is the error warning message that we want to suppress. So let's just put it right here, like so. And then we will have another pragma, GCC diagnostic, tough word to spell, diagnostic push. And if we have a push operation, we will also have a pop operation, and let's put it at the end of our C file. So pragma GCC diagnostic pop, like so. And let's make clean and make. There we go. Okay, so let's test this. Yeah, it seems to work. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Okay, so now that we have our indentation function, we can begin coding on our pretty printer, which will print our tree to the console or to any file descriptor. So I'm thinking something like this. Let it be a void function, print tree, and the first argument is a regular file descriptor, so we can tell it to print it to the standard output, for example, or we can print to a file. Second argument is the starting point, the root of the tree. So it can be the actual root, or it can be some other part where we want to start traversing the tree structure. So this is it's a tree of type, let's see, of name, let's call it root with an underscore. And what else? That ought to be enough, right? So before we do much of anything, I want to create the function declaration so we don't forget that. So we are below here, and this is a void print tree, which takes a regular int and a pointer to a tree, like so. Alright, so how do we do this? We need to have two for loops where we iterate through the tree structure with one of them, and if we find any leaves,
connected to that node, we will traverse that as well, while printing everything as well. So let's start by defining an int8 indentation, and we need to have a node n and a leaf l, like so. And let's see, we need some kind of a buffer as well, some intermediate structure that we can use before we print to the screen. So let's do int8 for consistency. So buff 256, and we do also need a size t, so an integer which we'll use to calculate the length of the string. But let's do int16 for that. So we'll call this size, and now we probably have what we need. So the first loop, we will set the n, which is a node, and what we have as a root is a tree. So we need to convert this to a node. So n equals the underscore root. That's our starting point. And for how long are we going to loop? We're going to loop as long as, let's see, as long as n, what's it called? And west is the downwards facing point. So if this is 0, then we're done. So as long as n west is positive, and we will set n equal to n west at each iteration. And what we're going to do when we get to this point, we will craft the beginning of our buffer. So let's see, we can use string copy. First I want to zero it out, by the way. So let's do 0 buff 256, and then we string copy into this buff, so we need to convert it to a char. And what is the first we want to put in here? So let's see, we also need to set the let's do it above the starting point of the indentation. So let's set it to 0 at the start, and let's modify our our indentation function a little bit, because currently we check that n is greater than 0.
I think it will be easier if we allow it to be 0. So let's remove this definitive restriction, and instead we'll check the first thing we do, that if n is less than 0, then we set n equal to, no, let's do this. If n is less than 1, then we simply return an empty string. And we need to encode it as int8 pointer. But that must be the best way of solving this. So if it's less than 1, then we just give back an empty string and assert that n is less than 120. Yeah, that's correct. Okay, so where were we? Up here. So we set indentation to 0, and then we can simply string copy into the buffer our indent function with our indentation. Because if it is 0, which it is from the start, then we will simply return an empty string, and this will try to copy an empty string, which will result in a no operation. So that's all fine and well. So let's see, we have created the indentation. Let's calculate its length. So size equal to, and we want the int16 representation of string length, and to string length we send the char representation of our buffer, and this should result in 0 at the first run. And let's just do if size is not 0, then we write to the file descriptor the char version of the buffer with the size. So this is our way of printing out the stuff. We will string copy, we will 0 it out, string copy, calculate the size. If the size is positive, we will write to the FD. Okay, so let's continue with our print tree function. Since we are using the same 1, 2, 3, 4, 5 lines every time we want to print something to the screen, let's factor out this into a macro, right? So let's go to the .ah file and find a suitable place for the macros. Let's do it right here, and we paste this, and let's see. Okay, so that didn't work. Let's keep this indentation. Okay, so what do we want to call this stuff? Let's say something like print, maybe. And we're gonna have a couple of arguments, right? So what do we have here? 0 the buff, that will be the same. Then we have the string copy to the buff. This indentation will change. So let's put an X here. And then we remove this stuff. And we just put X there. And you don't really need the parentheses, but it's good to always use parentheses when you refer to this argument, because in some instances it will be necessary. Okay, then we calculate the size depending on the buffer. That will be the same. We double check that the size is what it is, and then we write to the file descriptor. That will be the same, the buffer, the size. The only thing changing is this X. And since this is a macro, we will have to put this slash at the end of the lines. No, not curly braces, slash. Slash. But not on the last line, and we don't need this semicolon at the end either. So let's save this file, and then we can simply remove all this, right? And instead we can simply put print indentation. No, the function is called indent, but the argument is called indentation. And then we do like this. And we also have to increase the indentation. So let's just put plus plus right here. So the first round it will be 0, and then it will auto increment right here. Okay, so now we have printed the indentation to the screen. What else do we want to print to the screen? Well, we are in the first node, so we should print the path of the node. So let's see what we have. We have it's called path. So then we can just copy this line and paste it like this, and we remove everything inside of here, and then we just type, let's see, we have n for the node, and then path, like this. Alright, so these macros are really helping us when we need to repeat stuff. Okay, what's the next step? Now that we have printed out this stuff, I do also want to print out a new line, like so. And now we can get to the actual leaves. So let's do let's see. First we need to check if there actually are any leaves at all at this node. So let's simply do if n has any nodes, and what is it called? Let's see, the nodes, the leaves, the leaves are connected to the eastern link. So if n east is
non-zero. Then we want to do another for loop. And this time we will take the L equal to N east. And what do we want to have as a condition for this loop? Well, it will look kind of the same as above. We want to check that the leaf and that it has something to the east as well. So if it has something to the east, then we go on looping. And let's see if it has something to the east. So if it does not have something to the east, it will not run at all, right? So maybe we should simply do L here instead. So if we have L, and each iteration L equals L west, like so. So we set it to the east, and if we have something there, this will be true, and then we do this. What about the nodes? Did I think correctly there? So if we have this node, let's see, we check that if we have anything to the east, west even, but if we don't, we still want to process this root. So let's do like we did with the leaves instead. So n equals node root if n is true. Let's try this. Okay, so what are we going to do with this loop then? Let me just put this at the end instead, like so. So basically here we want to do the same as we would with the indentation, with the path, and so on. So let's see. We first want to print the indentation, but the indentation, has it changed? Yes, it has changed. Okay, perfect. Then we can simply do print, and we do indent according to indentation, like so. And after the indentation, we want to print the let's see what it's called. We have the key and the value. The key and the value. So basically we want to print, let's see, we want to print the node's path and add to it the key. I think that would be the best. So let's print n path again, and then we print I don't remember if this ends in a backslash. I don't think so. Well, that'll we see. So for the sake of it, let's front slash, let's print one of those as well. Then we want to print the key of the leaf, so L key. Then we want to print let's see, a space and some kind of arrow perhaps, and then let's do a single quote so we can show the value in a good looking kind of way. Then we have the L value, but that we need to do a little bit differently, I think. Yeah. That's right. I think we need to do it manually this time. So we write to the FD. And why do we need to do this manually only here? Because we don't know firsthand that this how big this value is, and we don't know, but it's not zero terminated, not necessarily anyway. But we have the size here, so we can use that directly instead. So we just print to the FD the L value, and we give L size as an argument. And perhaps we need to turn this into a char and this into an int, maybe. Something like this. And then at the end we want to print out, let's see, it'll be a single quote and a new line, right? I hope I'm getting this right. Something like this. And then I'll just put a return at the end like this. And are all these lining up? This is a for loop, and this blue thing is this for loop, and then we have the if condition. Okay, so let's save this, and let's go to the end of the file, and inside of this main, where we have some things already, let's see, let's remove this one. I don't have my key bindings right here. Well, let's do it manually. Like so. And do we have any additional print? F, we do. Let's remove that. And we do already have an, okay, this we need to remove too. Like so. And we have a tree here already, a small example tree. So before we free that variables, memory allocations, let's just do print tree and root like this, I think. Let's see what happens. We probably need to do some troubleshooting in this case. It's a lot of moving parts, right? So this, and let's do make clean. Jump down a little bit, clear the screen, and we run make. Boom. Okay. And as usual, I think most of these have one cause. So let's see, on line 21, pointer targets in passing argument 2 of string copy differ in signedness. Okay, and it's inside of our macro, right? So what does differ in signedness mean? Well, you can have a variable signed or unsigned, and the signedness is basically that possibility of a minus sign. So if it's a signed variable, you can have negative numbers, and in an unsigned, you don't. So this has to do with my own integers. I have int 8, int 16, int 32, and so on. So that's why I need to cast so much. And let's do that in this instance too, because this will always be a char pointer. So let's just do this, and that should be it for that error. So let's jump down, make clean. We don't really need to do make clean every time though. Make, okay, that's quite a lot less. So let's see, warning assignment to leaf from incompatible pointer type. And what is that? L equals L west. So how did I define L and L west? Let's see, where is that? The second is this one, L west, is a tree, right? That can be both a node and a leaf, but we shouldn't really target that in this case. So that's probably what's wrong. L west. Let's see, we need to go to the right, and to the right is east, like this. And N is also east in this case, and if N east, but here it should be west, because to the west we have all the nodes linking up, and to the east we have the leaves. Okay, let's try it again. So let's see, we jump down and we run make. Alright, not many left this time. So what is this kind of, oh, that must be a typo, right? 159. So 159. Yeah. Okay, let's see if it compiles now. No, now we got a couple of other errors. Argument 1 of print tree makes integer from pointer without a cast. Right, we need to cast that one, because that is a tree and we are treating it as a node. So let's see, go here, and I accidentally closed that file. There we go. So let's see, print tree, it wants a node, I think. Let's check the signatures. Print tree, no, it accepts a tree. Oh, but it wants an int as well. Ah, right, that's the one. So we need to put the FD. And what is the FD for standard output? Well, you can think like this. First is the input with the keyboard, so that's 0, and then we have the standard out, and then we have the standard R. So in this case, it's simply the 1, like so. And we go back and we compile, and we are compiled. Very nice. But let's see if this actually works. So let's start this up. And what did we call it? Simply called it tree. Okay, now we're talking. So we have the root, then we have the users, we have the users login, and inside of users login we have a leaf called John, and if we check the contents of that key, we get this string, and it looks kind of random, but if we go to the code and we check what we did put in that, we have this, right? So it works. But what about me? I was left out. Why is that? Okay, so let's try something different. What if we begin at the last leaf on the branch and we travel to the left instead? So if we set L to, let's see, we do have a function called find last, and I think we only need to give this a starting point. Let's check the signature. So it's an alias for this, find last linear, and it takes a node. So we give it N, and we loop as long as L, let's see, as long as L west. Let me think. Let's move this down a little bit. So, what if we were to loop until L west is not 0? When is L west not 0? Then we are at the node, right? Let's try comparing this L west. If this is not equal to the N. Yeah, we need to try something, right? And at each iteration we go to the west instead, until we've traveled to the last leaf before the node, right? So let's check if this works. Let's recompile this stuff. Okay, what is it saying? Comparison of distinct pointer types lacks a cast, but that shouldn't be needed, right? Because it's a tree. Okay, so let's go to the code and let's compare. Let's see, L west
this is a tree and this is a node. So let's turn this into a node instead, like so. And we make clean, we jump down a little bit, we clear, and we try again. Okay, that's better. So what is it saying now? Assignment to leaf from incompatible pointer type. Okay, it's the same thing there, I guess. So let's see. L equals L west, and this is a tree. So this should be cast as a leaf. I think this is the best solution. Let's see what happens. We do make clean, jump down a little bit, we run it, no warnings, and it's segfault. Okay, so now I think I know why it's segfault. If we look right here, let's see, we set L to find last, but if there are no leaves, it will not find anything, and it will return 0. So that is making this crash. We need to create a variable instead. So let's create another leaf pointer and let's call it last. And let's add those so we can do, let's see, we will set last equal to find last of n, like this, and let me add this ending bracket as well so I don't forget it. And what else? Then we will replace this part. Let's see, we will do something like this. We will set it equal to last, but first we need to check if last is not 0, then we do all of this, right? So let's see, where does it end? There, like so. This should work, right? And this find last is most probably the initial error as well. So if we go to last, find last, let's see, find last linear. It's an alias for this one, right? And if the parent doesn't have any leaves connected to it, then we use our return error function to indicate that. But this does not return 0, right? If we go to the H file and check this ret error function, or macro rather, it sets the error number to 0 in this case, and then it returns the null pointer. The null pointer is set to 0, but it's an intermediate step, right? So that's why it's not working properly. Let's make our lives easier and just return a leaf version of 0. Like so. Save this one, we go to our code, and this is how it should look like. we are pretty printing our binary tree. We have the root, and then we have this folder and this folder, and inside of this folder we have Lucy and the value of Lucy. We have John and the value of John. So now it's working. There are a lot of interesting things coming forward. So next week I will do the second episode of our anti-denial of service tool, and we will also later on continue to this binary tree and add the hash table algorithm, so we have a more optimized way of searching the tree. And there will also be a live stream. I'm not exactly sure when, but soon. And then we will continue to create our in-memory database. So a lot of interesting things coming up. And if you like this video, please subscribe or give it a like. And thanks for watching, and thanks for today. Okay, sup guys. Today we're gonna continue and possibly finish our tree implementation, our binary tree. And we are going to focus on optimization today. And like the title says, we're gonna achieve this by creating our own hash table implementation. And I'm gonna tell you what a hash table is, but first we're gonna create a linear search method for our tree, so we have something to compare to, and we have something in case our hash table implementation doesn't find the right answer. So let's go into our code and create a lookup function. So basically we will have a key, a string, and we will turn that into another string. So our tree, example tree, looks like this at the moment. We are able to print this with our pretty printer from last time. If you haven't seen that episode, check out the link in the description. I will also link to the very first episode when we created our tree. So basically we have different folders, and inside of the folders we can have a key with a value, and that lookup function is what we are going to write now. So let's put it, doesn't matter actually, let's put it right here. And what are we going to return? Well, we are going to return a leaf, because that is what we are looking for, right? We have nodes connecting the stuff together, and we have leaves which contains one value. So we'll return a leaf, and we'll call this lookup with a suffix of linear, because this is the slow linear version. And all we need to provide is a string, so it's an int8 pointer towards an array, and we will call this our key, like so. And before we get into this linear lookup method, I'm going to create an alias for that. So like we did here,
with our find last leaf function, we just have a find last, which translates into the linear version. And when we have another version, we can change easily into that. So this is going to be our lookup function, taking one argument, and it will resolve to lookup linear at the moment with the same key, like so. Let me just double check that it updates, because I have been having Sociopath running for quite a while now. Let's see, look up. Yeah, looks fine. So, how do we look up something in our tree? Well, as I mentioned, our tree looks like it looks like this. So I guess I was a little bit fast there. We do need one more thing, right? Not just the key, because we can have the same key, a key with the same name in different places. We also need to have the folder name, the node. So two things. Let's go into the code and begin by altering this. So lookup of x and y. We will look up linear xy. And what is x and y then? Well, we have the key already. Before that, we will also have a path, like so. And the path we can easily turn into a node. So if we go to our, let's see, I'm not sure what we named that function. Let's go through here. So we have find last linear. We create node. We don't actually have a find node function. Perhaps we should create one of those. Yeah, I think so. Let me just add this new function here. So it's a leaf, which is lookup linear, and it takes an int 8 pointer and another int 8 pointer, like so. And let's also create this new function, and that will return a node. So what should we call this? Find node linear. And this will only take the path. And let's see, we need to create an alias for this as well. So let's define find node with an x, and we will, let's see if I can line this up. This will be find node linear with an x, like so.
Okay, so let's begin by creating that function. And where were we? Here. So we want a node, and we will call this find node, and we'll take the path as an in value. And how do we find this linearly? We need to add that suffix as well. Okay, so we need a pointer, a node pointer. Let's call it P. And we'll see what else we will need. So we do a for loop. We set P equal to the node representation of the root. And we are going to traverse this as long as P is true, and then P will be equal to P west. Because all the nodes are connected on the western or leftmost side. So let's see, what do we need to do at each iteration? Maybe we can do something like this. We will create another pointer which we call ret, and we will set ret equal to the node of 0. Like so. And we are going to do a string compare. So if our P path is equal to our path, what do? Well, two things. We set return equal to P, and we break. And then at the end we simply return ret, because if we failed then it will remain 0, and if it worked out we will have our pointer right there. So let's test this out on our tree. So let's see, what do we have here? We have users login. Let's create a new variable, node test, and after we have printed our tree, let's just do printf pointer of find node, and the int 8 representation of the string users. Let's take log out first, so it should return a 0, right? Because we don't have a folder like that. Oh, what happened here?
Pointer targets in passing, argument 1, string compare differ in signedness. Does it? So p path and path differs in signedness. Let's see. So where were we? Create. No, not create. Find node. Path is an int 8 pointer. We need to send these as chars. That's why. Because both of these are actually int 8 pointers. Like so. Do test unused variable. Control reaches end of non-void function. 104. That's probably just because we didn't finish the lookup function, right? Yeah. I accidentally closed this one. I'm too used to doing WQ when saving. Right. Well, I want this to the left. Let's see if it compiles without warnings this time. So we make it clean, we clear, we make, and boom, it works. Maybe. Yes, we get nil. And if we supply this function with a real path that we actually do have, so instead of log out, we call this log in, because we create that right here. So if it works, it will return us a pointer. And it returned us a pointer. Alright. So now we can find our nodes in the tree. Next step is finding our leaves through this lookup function. And when we do the lookup, the first step will be to find the right node. So n will be equal to find node with the path. And if n is 0, we return the leaf representation of 0. Otherwise, we continue. So now we have reached our node. The next step is iterating through the different leaves connecting to this node and finding the one where the key is right. So let's do like we did in the last function when we find a node, only we do it with a leaf instead. So let's call this L, and we create a ret variable as well. Okay, so we do a for loop
and we set the leaf. First we set ret to 0, and it needs to be the leaf representation of 0, and we set our L equal to our node's eastern side, because that's where all the leaves are connected. So we begin there, we iterate as long as L, and each turn we do L equal L east. We continue eastwards until we are done. Yes. Then we do a string compare again. And this time I remember to cast those values. And what do we check for? We look at the leaves key. And is that equal to the char representation of the key with small letters? If anyone knows how to disable caps lock on a Mac, please tell me in the comments, please. Okay, so what are we doing when we find the key? Well, we set the return equal to L, and we break. And that's basically it. Now we only need to return this stuff, because the only thing we are doing with this function is finding the leaf. So lookup is not a good name for it, actually. Let's change this to find leaf. That's better. Then we can create a separate lookup function which will use this function and return string. So let's see, we have lookup and we want it to be find leaf. Find leaf. Find leaf. And find leaf linear, like so. Did I miss anything? I don't think so, right? And then we can write our lookup function as well, and that will return an int8 pointer, a string. So lookup linear, and in this instance as well we do need a path, and we need the key. And let's see, we create a leaf we set p equal to find leaf, the path
key, and then we return, if p is true, we return p value. And if it's not, what do we return then? Let's return an int 8 representation of 0. Alright? And we will add it here as well. So int 8 look up linear. Perhaps we should, in this case, actually specify that we want to use the linear one. So lookup linear, and we need to have an int 8 pointer and another int 8 pointer. And like before, we need to have an alias. So define lookup x and y, two parameters, and we will translate that into lookup linear with x and y. Like so. And it works. Let's double check that, by the way. So we are sure that everything works. So how do we do this? Let's just let's do something like this. We create an int 8 pointer towards a temporary string. Can remove this one. And then we set our test equal to the int 8 casted version of some key. So let's see, what do we have? We have Lucy and John. Let's do Lucy. And so let's, no, this is not what I wanted, by the way. Let's do it like this instead. We set test equal to lookup. And what do we want to look up? We want to look up the int 8 of users login and the int 8 of Lucy. Like so. And if test, we print it out. So
this, and else we just print no. That ought to do it, right? So we make, and we run. And we get the value, same as here. Cool. I want to see what happens if we misspell Lucy. Lucy turned into Luke. No, okay. And finally, I want to see also what happens if we get the name right, but the path wrong. Oh, it works exactly as intended. Perfect. So next step is we want to create a big tree, a really big tree, and we want to test it in there. So I need to find something on Google, and that is definitely not the right program. Let's see, there we go. There is a list of all the, maybe not all, but a lot of English words, and I need that list. So let's see, list of English words in TXT, and I don't really remember which one it is, but I think I will recognize the web page. 1,000 most, 10,000 English word list. This is the one, I think. Let's see. Word list without the extension. That doesn't seem very W-gettable, perhaps. Let's, oh, it's quite big. Let's rename it to wordlist.txt. So how big is it? 1, 2, 3. No, not that big. A megabyte almost. Let's see. Check the head of the list. Seems okay. The tail, and there are some characters at the end there. I don't like these Windows style things either. So there's a Linux command called call, which removes that. So you can do like call and from this to this, and then I'll just copy over the old one, the new one with the old one, like so. Still looks right. And if we open it up, now it looks good. And how many lines is it?
69,000. This would be perfect for our tree. So my take is we will create one node, so one level. We can use the node we have, and then we connect all of these 69,000 keys to that node with some value. Doesn't really matter what value. We can have let's see, we can have the key as a key, and we have the value as the key twice. That'll do. So this is the next thing we will do. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Okay, so let's begin by creating our new example tree. So let's clean out this main function. We can remove practically everything in here. So we will have a let's see, a tree, which we will call our example tree, and example will be equal to example tree, like so. And I want to create a structure which looks like this. So we have the root, then we have a folder inside of the root which is called A. Inside of that we have a subfolder B, and then we have A, B, C, and so on through the whole alphabet. And that will be our folders or our nodes. Then I will parse this English dictionary, and I will fill the A folder with all the keys beginning with the letter A, same with B, same with C, etc. And then we will have a perfect tree for our calculations and tests. Alright, so let's create our function signature. This will be a tree sample tree void. And how do we do this? Well, let's begin by defining the signature. So the tree is called example tree, and we need a character or an int8, keeping track of the A, B, C, etc. We do also need a node, like so, and we need the path. So let's make this a string, path 256. And we begin by zeroing out our path. then we do a for loop where we set the node equal to the node version of the root, and we set c equal to a, and we're gonna loop as long as c is less than or equal to z. And at each iteration, what are we going to do? I think nothing, actually. Alright. So first we need to create the path. So in the beginning, the path will be equal to slash. And then we wanna, let's see. I think I will do it like this, by the way. So let's do C++. Okay, so C contains our character. So we need some kind of int as well. Let's do an int 32 of n. No, not n. X. And do we need to initialize that? Let's do it just for the sake of it. And let's calculate the size or the length of the current path. So x will be equal to the int 32 of string length, and into that we will send our char casted path. So this will be equal to 1 from the start. So then we will basically do path plus x equal to c, because c is our character, and we need to append this slash as well. So slash. So let's do a little space here, and we will do x plus, no, not plus, x plus. So we set it to the slash, and then we increase it by 1. So the next time we can just set it to C, like this. And the rest is already 0 initialized, so this ought to work. Let's do some debugging as well. Let's just print out the path, so we know that we're doing this right. Okay, so we have our path. Now we just need to create our tree. So n will be equal to create node, and I don't really remember the arguments for this one. So let's search for create node. We need a parent and a path. Okay. So let's see. We need to save the parent then in another pointer. So let's do P for parent. So before we create the new node, we set P equal to the old one. And then it's N equal to the, let's see, P and path. And from the beginning, yeah, that's no problem. Alright, so we create that node, and I think we are basically done. Right? So now we just need to return this tree. And since we always begin at the root, we can simply do return the tree of root. And this should possibly work. So inside of main, we set example equal to example tree. And then we print tree example. Does it have any additional arguments? Let's see. Print tree. Yeah, we need an FD as well. So let's see. Standard in, standard out. It's 1. And yeah, this should be good. And then we'll simply free our, no, we can't really do that. Maybe we should create a function that frees up this stuff, but not right now. Let's see if it compiles or if we did mess something up. Make, let's see what we have. Oh, isn't this beautiful? This is art, but there's a double slash at the beginning. Other than that, it looks pretty okay, right? I don't remember though, do we have to have a ending slash when we create the node? I don't think so. Well, that will be, we will see that if that is the case. Let's go to this again and remove this printf thing. So why does it give us a double slash? Yeah, because we add this here. So perhaps we should simply begin with a let's just remove this and see what happens.
Okay, this looks better. This looks kind of perfect actually. It's beautiful in a weird, nerdy kind of way. Okay, so now we have our nodes. Next step is our leaves. So where should we put all of that stuff? We might need it later on, so let's create a function for this as well. What should we call that? We are going through a list of strings, and depending, well, this is another example function, isn't it? So let's do an int 32 of example leaves, and let's do the signature right away. So int 32 example leaves void, and let's highlight these examples somehow so we easily find them when we want to clean up, if we want to clean up. Okay, so what do we need in here? We need an FD so we can open the file. We need a let's continue on with int 8. We need a buffer. Let's do 256. We also need a leaf L. We probably need a node as well, and we need a character like so. And how do we move these on a Mac? No, not that. Where did we go? Well, let's do it the old-fashioned way. I want to have the same types of variables at the same place, basically. This'll do. Alright, so how do we create a leaf? We have a create leaf function, right? Create leaf. Let's do 2dd, paste, and we go to our main and above. Let's paste it here, turn it into 8 comments, and give us a little bit of space to work with. Okay, so we need a parent, a key, a value, and a count. The count being the number of characters in this. Alright. So I'm thinking we don't really need the, well, yes we do. We need to calculate the path somehow. Do we have to make it like a folder structure. Actually, yeah, let's do that, by the way, because that is how it will work in the end. So it's best not to change that. Okay, so then we need a little helper function creating a path. Alright, so let's call this int 8 example path, and we take in a character. And let's create our little signature as well. And this was an int 8 pointer example path. And it takes in a regular int 8. And what do we need here? We need an int 8 buff 256, and let's do basically like we did before. So we zero out the buff, and we need a, let's rename this, by the way. Yeah, okay. So we can create an int 8c, and we do for loop, where we set c equal to a. We loop as long as c is less than or equal to path, and C++ again. And what do we do at each iteration? We still need to use an int32 counter for the length. So x is equal to the int32 of string length, and we give it the buff, like so. Then we go to the buff plus C++ and set that equal to, no, not C++, X++. Let's see, buff plus 1, yeah, I think this is right. We set this equal to a slash, we copy this line, paste it twice, remove the plus, and set this equal to C, like so. And then we need to return the buff And I do not want to malloc this because we'll be calling it a lot. So let's do this statically instead. Okay, I feel like I forgot something, but let's try it out. Example path int 8. No, it should not be. See, let's try it just by doing let's do printf s, and we want to do example path of the letter J, and return. Let's see if it compiles. Nope. Warning, unused variable. Oh, never mind that. We're not done with this function. Okay, so let's see what it says. A, B, C, D, E. Okay, so it looks fine. I'm in a roll today. Not a lot of troubleshooting. Only working stuff. It happens sometimes. Okay, so now we can produce this stuff. Now we just need a variable to store that into. So let's do int 8 and path. And we will open up the file. So let's do the regular open. Example file, and we want to open it as read only. I think this is enough. And let's do assert fd, and what else? Yeah, we need to define that. So where do we have our constants? Do we have any? Yeah, we do. So we define our example file as wordlist.txt. And then we can have a while loop perhaps. So, and we need some kind of integer. Let's do int 32. What characters do we have left? X. So we set x equal to read fd buff 255. Before that we will zero out the buff. Like so. And let's see what the return value of open is. Of read. Man to read.
On success, the number of bytes. Let's see. Well, let's continue on as long as it's positive. And we need for the open a couple of includes, perhaps. I don't think we have this one since before. So let's add this one here. Alright, so we will loop as long as this x, let's do another set of parentheses, is greater than 0. And what will we do when we have read some data? I wonder if we get, we do get the new line. So let's begin by getting rid of that. So let's see, buff, no, I need to check this. So if we have A, B, C, D and a new line, then we have indices 0, 1, 2, 3, 4, and the string length in this case is 5. So what we need is buff plus x minus 1, and we set it to 0. So now buff should contain the correct word in question. And then we'll need to calculate the path. So the path will be equal to example path, and we send the first character on a buff. That's the only argument, right? Yes. So then we get a string back with the path to the node. That's one step. The next step is to find that node linearly. So n will be equal to find node, and what are the arguments for that? Find node. It's only the path, okay? So n equal to find node path, and if we don't have an n, then we simply continue. But before that, we will do one other thing. I want to zero out the buff again. Like so. And if we have an n, then we can create our leaf. So let's copy this down.
So L is equal to create leaf, and let's see, the parent will be the N, right? And the key is the buffer. But we also wanted to have the buffer twice as the value. So let's create a helper for that. Int 8 duplicate, and we take in a string, int 8 buff 256, we zero out the buff, we copy the let's see, into buff, into the char representation of buff, we copy the char representation of string with a maximum of 255. Then we set n equal to the int 8 representation of string length of the char representation of buff. So we have the length of the string. Then we do our next copy. And we need to do one security check, by the way. Let's see. X equal to the let's not make this so small. Let's do both of these at 16 at least. So the int 16 of the string length. Okay then, let's continue with our tree. So let's see, where were we? We're creating our duplicate function. So we are calculating the string length of the let's see, it's the this should be string copy. Yes, it's the key. We are calculating the string length of the key, but we are also calculating, let's see, the x will contain the n times 2. And if x is more than 254, then we will simply return buff as is. And if it's not, then we are going to string copy to the char representation of buff plus n. So at the end, past our current buff, and then we will copy, let's see, we need to do string dupe, because it doesn't like when it copies from the same variable to the same variable, usually not anyway. So that's why we do a string dupe here instead. And the source is going to be buff. String dupe buff. And we also need to specify a length, and this will be 255. So then we have the duplicate of that specific string, and we can simply return buff. This should be right, I believe. We do, however, need to make this static, because we cannot return. If we didn't make this static, it will be allocated on the local stack for this specific function, and that the memory is not really accessible from the rest of the application. But by making this variable static, we are moving this variable to the BSS section, the uninitialized data section, and that is accessible everywhere. So that's one way of returning a kind of local variable. Alright, so this should be able to duplicate a string. Let's just double check that real quick, so we are not coding on something which will fail in that kind of way. So let's just print out S, and let S be the char representation of what did we name it? Duplicate? No. Yes. Duplicate, and this requires an int 8, and then some string. Hello. So if we have coded this correctly, it should print out hello, hello on the screen, right? Let's do return 0 here, and I'm not sure if we have a half function somewhere which might get us into trouble, but we'll see, right? Yeah, okay. What does it say? Warning, while clause does not guard ... this statement, but the latter is misleadingly indented. Well, error, continue statement not within a loop. Okay, I must have put a semicolon badly somewhere. And this should most definitely not be there either. This is inside of the function, okay. So where does it end? Or where does it begin? This while loop looks a little bit lonely, doesn't it? So let's see. Then we have this right here, and we need to return something temporarily, right? This is an int32, so let's return the int32 representation of a 0. Then we end this function. Okay, let's see what it says this time. Okay, a little bit better. Error, too few arguments to create leaf. Well, we are not done with this function quite yet. Yeah, this is where we are. Okay, let's just remove this for now. Two unused variables. Don't care about those. So let's run this. Hello, hello. Okay, perfect. It works exactly as intended. So let's, well, we can wait a little bit there. So where are we? We want to create a leaf. Let's see. Yeah. And we have given it a parent, and we have given it the key. The next one is to provide for a value. And I think we will rename this duplicate function, by the way, because I don't want this in the final implementation. So let's add this example prefix to it. And did we create a signature? I don't think we did. So this is an int 8 example. What did we call it? Example duplicate. And it takes an int 8 pointer, like so. So when we call this function, we are going to use our example duplicate and give it the buff. And what else do we need? The next one is, let's see, we're giving it the key and the value, and we need the count as well. Let's just do int 16. This will be a little bit too unoptimized. Let's at least create a pointer. So let's do, what should we call this? This is the value. So let's do val, and we'll just do val equals, and then we can refer to it right here. So we send the string length and the char representation of val. That ought to do it, right? And then we have created our leaf. Is there something else we need to worry about? I don't think so, right? So this will loop as long as we have anything in this file. Then we will want to close our FD, and we want to return the number of leaves, right? So let's do a variable for that. Or do we have one? X? How do we use X? We haven't really. Yeah, we did. No. Let's search for X. There. The X is the length, alright. So let's just name this Y then. And we zero this, we set Y equal to 0. And at each iteration, we just do Y++. And then we can return y at the end here, and we don't need to cast it, like so. Okay. And this name of the function is example leaves, and it takes no arguments. Right. So let's clean this up a little bit. Example equals example tree. Will not yet print the tree though. We will, however, let's see, in 32x, and let's print some kind of message. So printf populating tree dot dot dot, and let's flush the buffer so it prints it instantly. Then we set x equal to example, what was it, leaves. Print out done. Something like that. And after the tree has been populated, we will print that tree to the screen. Okay, let's try this out. See if we missed anything. Make. Okay, something is wrong. Operation on val may be undefined. Why is that? Is it because we're using a static variable? I think we should be okay. What else do we have? Variable x set but not used. And that is 265. I just want to check why we never used that. 265. Set but not used. Right, we're not printing it or anything like that. Okay, let's just do this. What length we go to make GCC happy. Warning, val may be uninitialized. Val will be uninitialized. Okay, that's the price of being lazy, I guess. Well. Let's move this then. And we'll put it somewhere right here. And instead of this whole thing, word. So we have buff. Let's see, we have n, we have buff, and we have val. This should be the right thing, right? Yeah. So let's make clean, space down a little bit and make. And this time it is only complaining about unused variables. I can live with that. Okay, let's see what will happen. Okay. Why does it print like that? Let's see it from the start. Populating tree, and then it prints some stuff. And A, we have A, and then did we add some weird printf somewhere to see if populating tree done? Slash standard out x equals example leaves printf done, and then we print tree. What happens if we don't print the tree? Then it looks quite alright. So we print example. I wonder if it's the printing function or the creation which messes up this stuff. Let's see the example leaves function. What do? We open the file, we zero this, we read, and we create an example path. We find the node. Wait a minute, let's see. And if we don't find the node, we continue. Okay. But if we do find it, we do this. Right. We should zero out the buffer, but I don't think that is the problem, actually. But let's do it anyway. Let's remove this message. I thought it would take longer than it actually did. And we don't want it to complain about this, so let's void the x. And let's see what happens this time. Perhaps we should pay some attention to the warnings as well. So what do we have? Variable L set but not used. 236. So 236. It's inside of the example leaves. But we're using it here, right? We are setting it here, but we are not referring to it. That's right. But we shouldn't need to. Let's just remove that then. Leave L. And what was the other warning? Unused variable C 233. So we go to 233, and it's here. Okay, so the C, what did I think about the C? I probably thought of using that. Let's see. In order to check what path to put it on. But instead I referred to the first character of the buff. So let's remove C. Okay, let's see if it looks better this time. Let's make clean, clear, we make, and we run this thing. Okay, it does print a couple of these nodes, but it looks so weird. First we have the root, then we have /a, that's okay. Then we have /a, that's probably the first word. But then it all gets messed up. Why does it jump all the way to W? And what about the stuff in between here? Maybe we need some debug messages when we populate the tree. But before that, let's try doing a lookup on something. Let's see if we check the head of the file. Let's see if this aardwolf is in the tree. So how do we do that? We call the function lookup, and what are the arguments? It's the path, and the path should be the int8 representation of /a/ this, right? Or we need to separate those. So let's just do /a, and then this on int8 and that. I think it's like that. Let's double check the documentation, i.e. the H file. So we have this lookup linear, it takes an int8 and an int8. That's right. And I think this should be it. I'm not sure if we should have a trailing slash as well. Well, we'll see. Let's just do something like int8 p, and p equal to this. If p printf p else printf no. Okay, let's see how this goes. Example set, but okay, that's no problem. So let's run this whole thing. No, it does not find that one. Okay, we're getting closer. Let's test this out as well. No. Okay, so the problem is when it inserts itself into that tree. Let's remove this for now. This is a neat trick, by the way. We can use the preprocessor to do an if statement, and then we just end if. So this piece of code is not even in the compilation process. Alright, so how do we debug this the best way? I think before we create the leaf, we just print out the different variables. So we have something which equals something like so, and let's do something like this. And what do we have? First we have a node. And how do we represent that node? We can, let's see, node equals to, let's do not a pointer, but we go into the n and show its path. The next one is buff, that's easy. So buff equal to %s and buff. Then we have val, same there, val equals to %s and val, and finally we have the length. So we do len equals to %d, and we will simply just copy this whole thing. Put it right here. Okay, so this gives us a little bit of debugging information, and not so little actually. Alright, let's see what we have. And let's run tree and pipe it to more. So node equals /a, that's probably right. Buff equals to an a, and then all of this. Is that so? Okay, now I see. Oh, stupid me. The open and the read function doesn't behave as the fgetS function and the fopen functions. It does not read one line at a time, it reads a lot at a time. So we need to parse that on the basis of new lines. Right. Maybe we should just make our lives easier and use the library functions. It's only an example function, which will not be included in the final implementation. So let's do that. So where is it? Example path. example duplicate this one, example leaves. So let's comment out this one. Thought I had a key for that, but no. And let's do a file pointer as fd instead. And we comment out this one, and we do fd equal to fopen example file, and we do the read flag. We assert fd, that's okay. We clear the buff, and instead of this one, we will do, let's see, we will use fgetS to get a buff 255 from the fd. But what does fgetS return? Let's check it out. Return value of fgetS returns S on success. That's a string, right? Where is it here? S. Right, it returns the buffer. And I need the size. Okay, so one additional step then. So let's just transform this. So while fgetS is true, we do all of this. We temporarily remove this one. There. Okay, so we need to calculate x ourselves. X equal to the, how big is it? In 32, I think? No, it can't be. 8, maybe. No, it's 32. So the int32 representation of string length, and we don't need to do this. Just put buff right here, because buff is already a, no, it's an int 8, okay. So then we need to cast this as well into char. And also when we call fgetS, we would need to do this as a char, and the rest is okay. And then at the end we will fclose fd. I think I got it right. Let's see. No more errors, that's good. Let's do 3 and pipe it to more. Okay, this looks a bit more than I was hoping. So the node is this, buff is this, value is this, length is this, okay? Sounds right. Same here, same here, same here. Okay, this seems to do exactly that we wanted it to do. So let's remove this stuff. If 0. I don't want to delete it entirely because we might still need it. And then we go to our main, and we put all of this back. Let's run it like this, by the way, so we see if the lookup works. Make, we run 3, and we get nothing. We get nothing. So what do we have? Oh, okay, that's right. Let's put this back, because this is what we want, right? So make and run it, and it's a little bit slower now, you see, when we're doing it correctly. Okay, it says no, but I think I know why. That's probably because we have this trailing slash right here. So if we remove that, we should get the value of that variable. Yes, we do. That is correct. So it's the word Aardwolf twice. Exactly what we want. Okay, so now we can finally print out the... and I closed the wrong file. As usual, those vim commands. So let's get this down and this to the right, and now we will just delete this stuff, and we will print our beautiful tree, hopefully. So we do make clean, jump down a little bit, run make, sounds good, and we run tree. There we go, that's how it should look. Isn't it beautiful? Let's pipe it to more so you see more of it. Okay, so here we have all the different English words, and they are in the correct folder as well. What if we go down to the B? A long row down. Oh, here it is. So here we have the B words, and then we get down to the C words, and everything looks exactly as we would like it to. Okay, that's cool. So that's enough for this episode, I think. We will need one additional episode where we optimize this and go from the linear to better implementation. But this far, everything works. So if you like this episode, please like and subscribe so you don't miss the next one. And thanks for watching, and thanks for today.